So Christina, I'm just going to make you the presenter, okay?
Okay, but I think there are some other things first coming up, right? Some introduction.
Yes, absolutely. So,
hi, Madam. You're muted, Madam. I probably should be too, but no, I'm not.
Hello.
That's a strange background. Hey, how are you?
Hi, how are you?
I guess I did a talk for a student symposium and I don't know how to get it at the background now.
I just know how to keep this together. I have no clue about backgrounds.
I didn't know how to put a background in WebEx. I never used WebEx before, so you get to see my the room.
Christina, what time of the night is it then?
It's not very late. It's like 10 past 7.
Oh, okay, not bad. Okay.
A Friday
How
night. I'm not sure if I'm staying for your talk.
Oh, okay.
Also, because these days we are like on a 5 a.m. schedule.
Yeah.
Not exactly sure why, but we got in. But because before we were running programs that started very, very early, so we got into this early schedule. So.
Hello, good morning. Good morning, everybody.
Hello.
Hello.
Hi, Dilip.
Hello, Madan. Hello, Guru. Hello, Christina.
I share my screen. I've never done a screen share in WebEx.
Good morning, friends.
Well, there is a button at the bottom that says share.
Yeah.
So,
yes.
That's what I did.
Right. I think right now, yeah.
Absolutely. That's it. That's it.
Just let me make sure I can play videos. Can you see it play?
Yes. Yes.
Did you expect volume there?
No, I didn't. I rarely do that because then you have to sort of loop in system sound.
Yeah.
And I just finished a semester of teaching a class of 75 online.
Yes.
So
Hi,
I know what
Bhaskar.
this is.
You know better. Yeah, I understand. Even I don't engage in all such trivialities.
So, Christina, has your the teaching started in the university?
Well, I wasn't teaching this quarter, so it's still. So here there are quarters. So I started when this start late September, and it will finish in about 3 weeks, just before Christmas.
Oh,
yeah,
okay.
But, it's all online. I mean, I will remain online. I'm teaching next quarter. Next quarter, it will be online again. So yeah.
Oh, really? Okay. Wow.
Yeah, I was teaching in March because we went into lockdown mid-March, and then I was teaching then, but it was like towards the end. So
Right.
we've been working from home since middle of March. We are not we're not even allowed to set foot in the university.
Oh, really? Wow. Okay.
Theorists are not allowed to even set foot.
Right. Yeah. The same here. Yeah.
And actually, as of probably Monday or tomorrow or Sunday, one of the next few days, I think this part of California is going to go into an even more serious. It's going to go back to all restaurants closed, everything closed. So,
okay.
Because it's getting bad again. So, in Santa Barbara is not very bad, but we are regionally grouped with Los Angeles, and so then we.
Yeah. Wow.
So it's it's been a strange time. That's sure.
I know. Yeah. I see.
And you I guess somebody was saying they just finished teaching, so you just finished, I guess.
So
we just finished.
Yeah.
he just finished teaching, but for us again, the next semester will be online. The teaching was okay. It's just the way we had to do evaluations was very stressful for everyone, for the faculty and for the students.
Yeah. Yeah, exams are a problem, definitely. Yeah. We'll see. It's well, one of my daughters started graduate school this fall at Berkeley, and she hasn't even set foot on campus yet. So, it's, anyway. Mhm.
Hi, Krishnamurthy.
So for you, it's Saturday, right?
So,
For you,
I haven't been teaching in a long time. So, but those people that, for instance, Sriram has to goes to the department and teaches an empty class, because then it's
okay,
yeah.
I see.
But that's better. It's better. I prefer writing on the board and having a powerful camera which captures it than, do it this way.
Yeah,
That's
no.
right.
I mean,
I tried in the beginning because I was teaching a math course. I tried in the beginning to record it on my laptop, but the students complained of clarity, and they said, well, your voice is not okay, so you might want to do a voiceover. So now I'm not into video editing. So I said, you know what, let's get back to the tablet and me talking into a screen.
yeah.
Yeah, but it gets a bit of getting used to, because it's you don't feel free to talk. It's very constraining to talk to a tablet and a dark laptop. And of course, the minute you ask questions, you see that 10 people have got bad internet connections. So they just log off. But I guess it's hard for all. But
Hi, Sriram.
hello, Sriram.
Hi. Hi all.
Oh, Manoj is in his office.
Good morning.
Hi, Manoj.
Hi, Madan. Hi.
Yeah.
So I got delayed. I almost reached my office and I realized that I left my office keys at home. So
I don't even know where my office keys are. I haven't in a year almost. It's very funny. 2 days ago, we actually went out to a restaurant. You could go outdoors, and I realized it was the first time I wore shoes. I mean, proper shoes.
I'm wearing long pants still.
Are you sure? Should we see?
Don't
You can check. I mean, the jeans still.
Deepak, how are you? You are muted, Deepak. I cannot hear you.
Manoj, can you hear me?
Oh, yes. Hi. Just asking how are you? Haven't seen you for a long time. Okay. You're still in Japan, right? Sorry?
I'm in Bangalore right now.
Oh, you're in Bangalore. Okay. Fine.
Short visit, yeah.
We'll catch up later.
Sure.
Dilip, Sunetra hasn't come yet, right?
Sunetra is here.
Oh, hi, Sunetra. All right.
Hi. Yeah. Sunetra has to start the meeting, otherwise you won't be able to even log in.
Right.
Manoj, I'm going to give you the streaming link. Just take a look at it, okay?
Okay.
Everything is working according to me, but just take a look.
So I'll just click on the YouTube link, right?
No, yeah, just click on the YouTube link. Absolutely.
Okay, that's what I'm. Yes, you can see Dilip smiling.
Oh, I
No,
see.
no, there is a lag. There is a lag, Dilip. So don't get
Flag.
perturbed. Yeah, there is a lag.
Yeah. Keep the YouTube muted, Manoj.
Yeah. So what I will do is, and especially, I mean, of course, if do is as people keep asking questions here, of course, the speakers will be able to hear. But if there are questions on the live chat, I'll just collect it and put it on the chat. So the session chair as well as the speaker will be able to see it. Okay.
But
So
I
the
don't
speaker.
think I can follow the chat while I'm giving a talk.
Yeah, no. The sessions chair will just, draw your attention to it and read it out to you.
Okay. But I mean,
Yeah.
people are welcome to interrupt anytime.
Yeah. I think so. I think that's a very good thing to do.
Sunetra, just let me know when it is time to start. Okay.
Yeah, I think we can just wait for 10 minutes, right? Because people will want to log in and we've told that it's at 9. Oh, no, I think you should start now, right? Because the talk will start.
That's fine. We can
Time to
for
start.
a few more minutes.
Yeah.
I think
Yeah,
we're supposed to
few
start 10 minutes, right?
Yeah.
You guys are supposed to be making opening remarks now.
Right. You are in the middle. You're supposed to start 10 minutes.
Yes, I think you should start. Manoj, do you want to should I make you the presenter or it's fine, right? You should be able to.
So, Sunetra, so we can start now, right?
Absolutely. Get started, please. Thank you.
All right. So, dear colleagues within IIT and elsewhere, friends, students, good morning to you all. I hope I am audible. Right?
Yes.
Yes, ma'am.
Yes.
So many of us would remember that we started this set of meetings last December with an informal one-day event on soft, active, and living matter, and that was about an year after Aditi's untimely death. And the 2019 meeting started off with a plenary talk by Sriram Ramaswamy, who was also Aditi's PhD supervisor. And apart from Professor Ramaswamy's colloquium, last year we also had a number of shorter talks on soft matter and allied fields, delivered mostly by colleagues from various departments within IIT as well as neighboring institutes like NATS. And the meeting concluded with a remembrance session where various people recalled their association with Aditi. After the successful meeting last year, some of us have been thinking about trying to run this symposium as an annual event, at least in a minimal way, with mostly local speakers and a few newcomers. But then we are really fortunate that Aditi's parents, Professor Narasimha and Dr. Neelima Narasimha, stepped forward to support us in this endeavor by contributing a fund to run a meeting every year in Aditi's name. And the formalities were concluded and the setup was finalized. But just as we started the preparations for this year's event, the pandemic struck us, and then given the prevailing uncertain situation, after some discussions, we decided to hold an online event this year. And after a few deliberations, we converged on a half-day-long symposium with 3 distinguished speakers, and it is truly nice that all the speakers that we had approached agreed immediately, and that is how today's event essentially materialized. And once again, I would like to express our sincere thanks on my behalf, as well as on behalf of my colleagues who are members of the symposium committee, as well as the entire Department of Physics, IIT Madras, to all the speakers, especially Professor Christina Marchetti, our first speaker of the session, who kindly agreed to give her talk somewhat late in the evening, her local time, given the significant time difference between the zones. In fact, this was one issue we were a little worried about initially, but then she was kind enough to agree to give the talk in the evening. So the broad theme for today's meeting, as it was for last year's also, is soft active living matter. And I am sure that most members of this audience would not need any explanation of these terms. These are very well known already. But for the sake of others, especially students and non-expert members, I would just like to summarize in a few words. So any material that is soft to touch is soft matter. That's the simplest sort of layman definition one can give. And a little more technically, one can say that all materials that are easily deformed, moved by thermal fluctuations is soft matter. And that includes a lot of materials that we already hear about or are familiar with, including polymers, membranes, colloids, liquid crystals, living cells. And when soft matter is coupled to local sources of energy and driven away from equilibrium, it becomes active. And living matter is both soft and active, but of course much more than that. Of course, this may not really have conveyed much, but there is nothing to worry because we have 3 really wonderful talks lined up for the morning, with each talk focused on one of these ideas. And we were really lucky to find 3 speakers who would actually fit into each of these categories quite nicely. So I should also add one more sentence here, that this lasting legacy is in active matter physics, especially the hydrodynamic theory of active matter, which happened during her PhD work with Professor Ramaswamy, and that involves some of the most highly cited papers in the field. I now like to introduce the first speaker of today's symposium, Professor Christina Marchetti. Professor Marchetti is affiliated with the University of California, Santa Barbara, and is among the most well-known people worldwide working in the theory of active matter. In her long career, Professor Marchetti has worked on a broad range of problems in condensed matter physics and non-equilibrium statistical mechanics, including supercooled fluids, superconductors, and driven disordered systems. Currently, she is interested in the emergent behavior of active matter, with realizations ranging from the organization of cells in morphogenesis to the assembly of active colloids. A little more about Professor Marchetti. Professor Marchetti was educated in Italy at the University of Pavia, earned her PhD at the University of Florida, joined the faculty at Santa Barbara in 2018 after 30 years on the faculty at Syracuse University. She is currently co-lead editor of the annual reviews of Condensed Matter Physics and Physical Review X. She is a fellow of the American Physical Society and the American Association for the Advancement of Science, a member of the American Academy of Arts and Sciences and the US National Academy of Sciences. In 2019, she was awarded the inaugural Leo P. Kadanoff Prize by the American Physical Society. So I would now like to welcome Professor Marchetti to deliver her colloquium titled Active Topology. Professor Marchetti has indicated informally that she welcomes questions in the middle, although in the interest of time, I request that these be kept to a minimum. We have planned a 15-minute interval between talks, dedicated to questions and interaction. Professor Marchetti.
Thank you. Let's see. Well, make sure I can share my screen. Can you see my screen?
Yeah.
Yes, and you can hear me, right?
Yes.
Okay. Let me also do this thing here. Okay. So thank you very much, Manoj. It's a pleasure and an honor to be asked to speak here tonight, or this morning for you, night for me. I have a somewhat ambitious title here, Active Topology, but the reality is that I will mainly be talking about active nematics. And the image you see here is a computer rendering of what an active nematics will look like between cross polarizer. Is an image that was created by Luca Giomi quite some time ago. And the points where you see dark and light plumes meeting are the topological defects in the liquid crystal, which I will focus on, and that sort of drive this non-equilibrium dynamics. And so what I will try to do today is tell you about the non-equilibrium dynamics of active nematics and how we can actually describe this flow by focusing on the dynamics of the defects, so developing a description of the defects as active quasi-particles. And the reason I decided to talk about active nematics is because essentially it was in this 2002 paper by Aditi Simha and Sriram Ramaswamy that the system was really introduced and first described at the level of hydrodynamics. Has become a very popular system in active matter, but this first seminal paper here really is the one that kind of created the field. And of course, there's been lots of other, to me, very important papers that Aditi contributed to. But also, I actually had the pleasure of collaborating with her on this review of modern physics. Several of us, including Sriram, in addition to Aditi, and Madan, and many others, wrote back in 2013. There was quite a big effort, and Aditi contributed to it quite a bit. I have to say, I never actually met her in person, but at that time we communicated like this, virtually, although it wasn't quite as popular back then, but we did quite a bit of this. So she definitely played a key role in contribution to active matter, and I think it's fitting that we honor her memory today, talking about active nematics. So before we get to nematics, just I was told that there'll be students here, so just sort of a general slides on active matter. Well, active particles are sort of engines that consume energy to generate their own motion. And active matter is a collection of interacting active particles, so interactive engines that self-organize without a leader and in the presence of noise. And there are many examples on a broad range of scales, both from the living and non-living world, from bird flocking or collective animal behavior, to the organization of cells in morphogenesis, to the organizations of various protein and cytoskeletal filaments inside living cells, to so-called active colloids, which are synthetic realizations of active matter, and many more. But in particular, a lot of these so-called active particles are actually elongated, such as bacteria or birds, and therefore they can organize in liquid crystalline states with orientational order. Now, orientational order is something we are very familiar in physics and in soft matter in particular. And to the right here, we have perhaps the most familiar, sorry, to the left, we have the most familiar type of orientational order, ferromagnetic order, that is exemplified by ferromagnets, where as you lower the temperature in a ferromagnetic material, the spin is spontaneously ordered in a spontaneously chosen direction, and the material goes from a paramagnet to a ferromagnet. And in this case, the order parameter is the magnetization, the vector of the system. A perhaps slightly less familiar type of orientational order is that of nematic, which is apolar in the sense that the units making up the nematic are not vectors, but are head-tail symmetric. And as you either increase the density or lower the temperature, the material can go from an isotropy liquid, where these nematogens or elongated rod-like particles point in random direction, to enematic liquid crystals, where the rod-like particles are all oriented, or generally a preferred orientation. Now, in this case, the system is up-down symmetric. The orientation is characterized by a unit vector called the director, but it's really a double-headed vector. And so the order parameter is a tensor, often known as the alignment tensor, which is essentially a measure of the cosine square of the angle that these director form with a fixed direction of space. Those are so-called passive liquid crystals. Active liquid crystals are ones where the rod-like particles are active. And again, we can have active polar fluids, and bird flocking is like the traditional example. But what I'm showing here is actually a movie of active colloids, self-propelled particles that have a polar propulsion. And they're confined here to a racetrack. These are experiments from the lab of Denis Barthelot in Lyon. And as you see, they flock. And even there, you can even see two flocks colliding in this case and generating some kind of interesting dynamics. On the right, I have sort of the iconic example of a two-dimensional active nematic liquid crystal, a suspension of microtubules bundled together by kinesin motor protein. As the kinesin walks towards the polar head of microtubules oriented in opposite direction, it extends the two microtubules of the bundle so that they exert forces on their surroundings, generating, in the presence of ATP that feeds the kinesin, generating these self-sustained turbulent light flows that have been referred to as active turbulence. Now, in both active nematic, as you see here, you see quite a bit of nematic order, orientational order of the filaments, but also strong distortions, which are actually topological defects of the nematic. And in fact, even in equilibrium, order is never perfect when you quench a system from a disorder state to an order state, driving it through a phase transition. You get order, but the order is interrupted by topological defects, which are a strong distortion of order that cannot be removed via smooth deformation, and are truly fingerprints of broken symmetry in the sense that the energetically most favorable defects have a structure that depends on the broken symmetry of the system. So for in the case of polar order, the defects that are lowest in energy are vortices of charge, topological charge +1, or anti-vortices of topological charge -1. The topological charge is defined by the angle through which you have to wind the order parameter when you circle the defect core. And so in this case, the angle will be 2 pi. And if you divide that by 2 pi, you get the charge, which is +1. In a nematic liquid crystal, which is sort of field of lines as opposed to a field of arrows, the lowest energy topological defects are so-called disclinations. Here is the shape of a +1f disclination. Here is a -1f disclination. And if you can see that if you circle the defect in this case, the Older parameter only has to wind of pi to go around the defect once. That's why the fractional charge. And you can find examples of plus and -1f disclinations. If you look at the ridges on your fingers, the tip of your fingers, you can actually see them quite clearly there. Now, in equilibrium, we have a well-developed theory, essentially, of the statistics of topological defects. They essentially behave like Coulomb charges. Opposite sign defects attract, same sign defect repel, with an interaction which is very much like a Coulomb interaction. And in fact, many order-disorder transitions in 2 dimensions, continuous transitions in 2 dimensions, such as a superfluid, 2D melting, the transition from an isotropic to a 2-dimensional nematic, can be described through the so-called Berzhinsky-Kosterlitz-Thouless transition as defect unbinding transition. In other words, there is a well-understood mapping, again, of the statistical mechanics of the gas of defects onto that of a Coulomb charge of defect charges. And below a certain temperature, opposite sign defects are bound, and that will be the order state. And when you go above a critical temperature, the Kosterlitz-Thouless temperature, which depends on the stiffness of your liquid crystal, essentially in the case of liquid crystal, defects are thermally unbound. They unbound, so now you have a free defect gas, and the state of unbound defects corresponded to a disorder state. So again, the order-disorder transition corresponds to defect unbinding. This is probably stuff that a lot of the students have seen in classes. So what's different about active systems? Well, in active systems, first of all, defects become motile. This is especially evident here in the nematic by Zvonimir. This is, I think I forgot to say, this is from the lab of Zvonimir Dojek, who is now very nicely a colleague of mine here in Santa Barbara. You see here that the defects, you see these comet-like +1f disclinations and this triangular shape -1f, but in particular the comet-like ones are moving around all the time. They become motile particles. And in the movie to the left, which is again from the lab of Bartolo, so these are again these polar active colloidal particles. In this case, you see that the defects are sort of like rotating polar vortices that actually coarsen eventually to a single giant vortex here in the system. So the first thing that happens in active systems is that defects become motile entities. But even more surprising is that for certain configurations, it looks as if opposite sign defects actually repel. So here again is a snapshot of the nematic liquid crystal. You see here the -1f defect and the +1f defect at one time, and at a later time they moved apart from each other as if they were actually repelling. Why would expect opposite sign defect to attract, as I said before, like Coulomb charges? These are actually older experiments in a layer of vibrated granular rods in which Sriram was involved, and you see a similar kind of behavior here. Finally, one last reason for focusing on the effects is that it was pointed out more recently that in living systems where often nematic order is actually observed, topological defects like these disclinations of the nematic liquid crystal may serve a biological function. This image here is an epithelium, a layer of tightly packed cells with no gas between cells. These are particular experiments from the lab of Benoit Ladoux. And what they have seen in this system, they track defects. So here you don't see very well, but this is sort of like a +1f defect in the orientational order of these cells. And the plus 1f defect seems to be associated with the location of where cells actually get extruded from the 2D layer and eventually die. And similar behavior has been seen in layer on neuron stem cell by the lab of Masaki-Sano in Japan. In bacteria, these are layers of a bacterium called Myxococcus santos, which is really a rod-like bacterium that glides on soil. Again, you often see a lot of nematic order with associated topological defects. And what was established is that the plus 1f topological defects, again, are associated with sort of accumulation of particles and other places where the bacteria start forming a second layer. So in this image, the light color is actually empty space. The sort of beige color is a single layer, and the brown color is the second layer of bacteria. And the second layer gets formed starting at the location of the plus 1f defects. And finally, even more interesting are beautiful recent experiments by Karen at Technion on Hydra, a freshwater organism that can actually regenerate itself from a fragment. And the whole organism exhibits quite a bit of nematic order. You see here the alignment of the cytoskeleton fibers that are actually in the supracellular level here. And what Kindred was able to establish is that during the regeneration of this organism, there is a close connection between the location where, say, the tail and the mouth and the limbs of the organism form, and location again of either plus 1 or plus or minus 1f defects in this nematic order. In other words, the idea is that in this case, the topological defects serve as organizing centers for morphogenesis. So lots of good reason for studying defects. We know and love them in equilibrium, where we use them to understand phase transitions. They become motile, very interesting. They seem to drive the dynamics in active systems, and they seem to even have possibly some biological function. And so
Christina, a question.
Yes, please.
So in the myxobacteria, how quickly are they turning around? You know, because you would think that if they are bacteria that are moving in a particular direction, you might get polar rather than nematic structures. Are they reversing very frequently?
Oh, mixo reverses. Sorry, I should have said that. Absolutely. So mixo it's kind of an amazing thing. Mixo really travels back and forth, has a reversal time, and I forgot exactly, but I forgot exactly the time scale, but it's quickly enough that, especially at this high density, really you can see that the order is nematic. And by the way, the very fact that you will see plus or minus 1f these defects is what tells you, as you know very well, Sriram, that the order is nematic. That's the point about the defects. You know, in active systems, you don't necessarily know whether you might know something about the constituents, whether or not they're polar, but you don't necessarily know if they're going to alternate states with polar or nematic order. But the presence of the plus or minus 1f disclination is like the telltale sign that the order is nematic. And so, yeah, mixo reverses, especially at high density. So it's a very, yeah. Thanks. Any other question? Thank you for interrupting, by the way. It's good. Any other question? Okay, so what we embarked on, and by the way, Sriram, I will say this at the end, but Sriram was involved in part of this work, together with other people that I mentioned at the end, is in essentially deriving effective theory of, as I said, of defects in active system as quasi-particles. In equilibrium, this has been done a long time ago. In the context of a nematic, you could start with the Dejean, Ginzburg, Landau free energy, identify defects, energies, and interactions, and literally map the statistical physics of defects, as I said before, onto that of a Coulomb gas. Now, in an active system, we don't have a free energy, so we start with active nematic hydrodynamics, and I will tell you about that in a minute. We solve the equations for moving defect solutions perturbatively in activity, and we derive equations of motions for the defect's position and orientation. And what I'm going to show you is that in this case, we can describe the defect gas in the nematic as a mixture of passive and active charges. The -1F defects behave like passive particles, and the active and the +1F behave like active particles because of their cell propulsion, effective cell propulsion. But I will show you how we do this. Okay, so let's start with nematic hydrodynamics, passive nematic hydrodynamics. First of all, we consider a system on a substrate. So rather than writing a Navier-Stokes equation for the flow, we write a Stokes equation where friction with the substrate, gamma is a friction, is balanced by forces, pressure gradients, viscous stresses, and elastic stresses associated with the formation of the orientational order in the nematic with a stiffness K. Then, of course, we need an equation for the orientation for the order parameter, our alignment tensor Q. And the key property of nematic hydrodynamics is essentially that orientation is coupled to flow. Shear flows bend the order. Rotation also causes the formation of the order. And then there is a term here that describes the relaxation of the order parameter as a derivative of a free energy that contains a familiar quartic term that allows, we are in 2 dimensions, so the nematic transition in 2 dimensions is continuous. And so we don't have any cubic term, and this just drives the transition between the isotropic and the nematic state. And then we have a term that describes the energy cost for the formation of the order with a characteristic length scale, which is the nematic coherence length, is the length scale over which the system changes between isotropic and nematic. And I'll be working deep in the nematic state, so this length scale is a very short scale indicated here. In the case where you have a defect, is essentially the size of the core of a defect. Now, in an active nematic, in addition, you have what are known as active stresses, meaning in the case, for instance, of the microtubule bundles, when the bundles, the filament extend under the action of the kinesin, the bundles exert force dipoles on their surroundings, generating stresses and driving the flows. This is actually something that was indeed first described. Sriram will say it was done earlier, but I think the first time it was described properly was actually this paper, this 2002 paper by Aditi and Sriram. And so the active stress becomes proportional to the nematic order parameter itself, to the alignment tensor, to a proportionality that we call activity that will depend on, for instance, the density of kinesin, the concentration of ATP, the drivers of this extensional motion of the microtubules. This activity parameter alpha actually has a sign that depends on whether the forces are pointing out, as in this case, as in the microtubule suspension, which corresponds to extensile forces, or in my convention, negative alpha, or are pointing in, as they would, for instance, in an atomizing suspension, corresponding to positive alpha and contractile forces. But I will particularly refer here to systems where forces are extensile. So when you add an active stress to the hydrodynamic equation, that's really the only term that makes my hydrodynamic active. And that introduces an additional length scale here, often called the active length, which is essentially the length scale that you get when elastic and active stresses are balanced. And the square root of the stiffness to the activity. I should have put a magnitude here since my alpha is negative. And in general, I will be considering a situation where the active length is quite a bit larger than the coherence length, and they're both smaller than the system size. This is the situation where you get this kind of turbulent light dynamics that I showed you before. Now, going back to the experiments for a minute, these are again images from the Dogic lab of the suspension of microtubule bundles in 2 dimensions. And what happens is that in a bulk system, these active stresses render the nematic spontaneously, the order state spontaneously unstable through this bend instability, as it's called. and then eventually start giving rise to this more complex flow. Again, instability predicted in this 2002 paper I mentioned now a few times. At even higher activity, this band instability turns into these self-sustained turbulent-like flows with proliferation of topological defects. You see the comet-like +1F that are actually zipping quite rapidly through the system. Those are the red ones. And the triangular -1F, which are the blue ones, which are moving somewhat more slowly, but they are also carried along by the flow. Now, if you take this continuum hydrodynamics of epimematics and integrate the equations numerically, you can actually reproduce a lot of this motion. What is shown here are movies obtained by integrating the continuum theory. The image to the left in red and blue, the color is the magnitude of the order parameter, with blue being 0 and red being 1. And the segments are the director, so the directional order of nematic order. And then you see the topological defects. The +1F are dots, the -1F are triangles. And you see that topological defects are in the region of 0 magnitude over the parameter, because that's where the defects corresponds to normal regions. The image to the left represents the flow. The color is vorticity, with, I guess, red counterclockwise and blue clockwise. And you might notice that defects tend to be generated, tend to be unbound at the region where of large shear between two counter-rotating vortices. There's been a lot of people, especially, for instance, the group of Julia Yeomans and many others, doing a lot of work on studying the continuum hydrodynamics of these systems, lots of interesting things that I will not tell you about. But what our focus has been on asking whether we can describe these dynamics by focusing on the dynamics of the defects. And so the first thing that you note is that you can immediately understand why these defects become motile particles. Now, if I write down here a sort of a simplified version of the Stokes equation where I've neglected pressure gradient, let's say the system is incompressible, and I have neglected elastic stresses, so then you can really think as this active stress. Clearly, if there is a deformation of order, the active stress associated with that deformation can provide a source for the flow. And so if you insert here on the right-hand side the structure of Q corresponding to individual defects, you can calculate the flow field that a particular defect will generate. And a +1F defect will generate a flow field with these two counter-rotating vortices. The important thing is that the flow field it generates is non-zero at the core of the defect, and therefore this defect will ride along like a colloidal particle in a fluid with the flow it itself generates, with a speed proportional to the magnitude of activity, and actually a direction of velocity that depends on the sign of activity, so that in a extensile system, defects always ride along towards the head of the comet, and in a contractile system, they are directed towards the tail, which is very nice because it also provides you, remember I said that the presence of these declinations tells you that the order is nematic, and now the direction in which the +1F travels tells you whether the stresses in the system are extensile or contractile. And this is so when you in the experiments where it was seen that it looked as if opposite side sign defects were repelling each other, actually what's really happening is that the +1F defects is self-propelled for this particular relative orientation, is self-propelled away from the -1F, and so it can overcome the Coulomb attraction and the defects can move away from each other. I should have said that the -1F defect also generates a flow which is actually more complex, consists of 6 vortices, but due to its trifold symmetry, the velocity vanishes at the core of the defect. So to a leading order, this defect behaves like a passive particle. So a self-propelled particle, the +1F, a passive particle, the -1F. So excellent former student, Suraj Shankar, now a postdoc at Harvard, embarked in the derivation of the dynamics of the defects of quasi-particle in a more systematic way, by again starting from a simplified version of the hydrodynamic equations, where we only balance friction with active stresses, inserting single defect solutions, and then obtaining equations for defect position and orientation perturbatively in defect activity and defect speed. And the important thing is that clearly the -1f defect has an orientation. The polarization can be defined properly in terms of gradients of the order parameter, and with this definition actually points in always towards the tail, so in the direction opposite to which the direction in which the defect will move in an extensile system. But a full description will require, so in equilibrium, you think of these defects as point particles, but in active system, this becomes an active polar particle, which is self-propelled. Now, these equations to this perturbative order in activity and in this approximation in which we consider really the dynamic of a defect in the effective field of all the others treated as quasi-static, take on a relatively simple form. First of all, the defects behave like colloidal particles in a fluid, like overdamped particles. The -1f simply experiences the Coulomb force, or the elastic force, due to all the other defects. And in addition, we have some noise here, so it's dynamics described by a Langevin equation. The +1f defects similarly experiences a Coulomb force due to all the other defects, but in addition, it behaves like a self-propelled particle. It has a propulsive speed along its direction of polarization. And the direction of polarization is changed both by noise, but also by active torques. And the torque the defect experiences is one that tends to align the defect direction of polarization with, again, the mean force that the defect feels due to all the other defects. So again, this dynamics is really describing a gas of charges. Interaction are Coulomb type interactions, where the -1f behave like passive charges and the +1f behave like active charges. They're polar particle with a polarization, a self-propulsion, and an aligning torque that aligns them with the force that they experience due to the other defects. Now, what can you do with these equations? Well, the first thing you can do is consider a pair, a dipole, a neutral dipole, a +1f and a -1f, and ask what kind of forces, whether the forces acting on the defects can lead to defect unbinding, essentially. And if you do a simple one-dimensional model, meaning assuming the defects move along a straight line, you can recast the equation of motion for the relative for the distance between the two defects. In this simple form, you have that the rate of change of R is determined by the interplay between self-propulsion that tends to drive the +1f away from the -1f and the attractive Coulomb interaction. You can rewrite the dynamics in terms of an effective potential, which will have a maximum, where attraction balances self-propulsion. And so what this 1D model suggests is that any noise can actually drive this particle to go over the barrier. That is, any noise can actually drive defect unbinding regardless of the activity. This would say the actually nematic never exists because defects are always unbound and they're always destroyed. But in reality, the +1f defect does not travel in a straight line because it is an active particle and it experiences orientational noise. And so it has a persistence length. It travels in a straight line. My cursor is, I don't know, doesn't move anymore. It travels in a straight line over a distance, which is determined by the ratio of the propulsive speed to the strength of the rotational noise. and then rotational noise turns its nose away. And so if you examine the dynamics of a defect pair more carefully, including the noise, and go from Langevin dynamics and construct a Fokker-Planck equation for the probability for the pair to be at a separation R with the +1F having orientation E, you can actually solve that equation for the steady state probability perturbative inactivity. And you will find that essentially, if the noise is large enough so that the defect no longer travels in a straight line, then the defects essentially can remain bound. So another way to look at this is that the noise renormalizes the strength of the effective interaction between the defects. That remains Coulomb-like, but with a strength that is renormalized by sort of like the effective temperature of active particles that depends on the persistence length and the strength of the noise. And so what happens essentially is that the noise saves the nematic, resulting in finite unbinding threshold. In other words, if the persistence length is sufficiently short, which happens at large noise, so that the defect turns away from this straight direction before reaching the distance of the barrier, the defects remain, the defect can remain bound. And so this ratio of these line scales essentially identifies a line in the plane of activity and nematic elasticity strength that below this line, the defects are bound and one has a homogeneous nematic order. And above this line, the defects are unbound, and now you have this gas of active defects corresponding to the turbulent-like state seen in the experiments by Dogic. And these axes actually, in principle, are axes that one could tune experimentally, because one can tune the stiffness of the nematic, for instance, by tuning the length of the microtubules, and one can tune activity, for instance, by tuning the concentration of ATP or the concentration of kinesin motors. So even though we haven't tried to quantify this line in terms of corresponding to experiments, this provides an understanding of this active turbulence as an activity-driven, causalist-Tauless defect unbinding transition. But I would like to go back to these active torques a minute, that we found that the dynamics of this polar particle, which is the +1F defect, the orientational dynamics is controlled by a torque that tends to align the direction of polarization with the Coulomb force that the defect feels due to all the other effects that are around. We actually tried to compare this prediction with the numerical solution of the continuum equations by tracking defects obtained from the solution of the continuum equations and making scatter plots of the angular velocity of the defects with these answers from the torque. And it seems to work, even though, to say, this is work that was done by actually an undergraduate, which unfortunately graduated now. And we really need to do this a little bit more extensively, but it seems consistent with our prediction.
Christina,
yes.
What is Zio-phi here?
Say again?
What was Zio-phi?
The psi. So this polarization is a vector in 2 dimensions. So it's cos psi, sin psi. So the psi is the direction of the angle that determines the direction of the polarization. And so psi dot will be the angular velocity of the defect.
Thank you.
Sure. Anything else?
Yeah, Christina, just remind me, the numerical studies that Supavid did were for a case where you have incompressibility of the overall velocity field or not? I just, or is that too complicated a question?
That's a very interesting question. I can tell you more about it either at the end or another day.
Okay, cool.
These, there is no incompressibility. If you put in incompressibility, we have seen the opposite sign of the torque, and it gets complicated. This was without incompressibility, which is the case that we actually, for which we derived the equations. But there is a lot more to say about incompressibility. Okay.
The previous, can I ask the question?
Yes.
Where you in the previous section, right, where you essentially neglected all the viscous effects and then use the friction to balance the active stresses. And if you think about it, friction is really coming from the substrate, while viscous resistance is primarily coming from the regions on the sides. And if you look at the experiments, the fluid looks, it looks quite fluidy, in fact, particularly that of Dojic and so on. So the question is, should one worry about the role of viscous effects in these situations, or what would you think about the role of viscous effects?
So I want to say two things. First of all, I think the experiment, the fluid is most likely incompressible, and we did not impose incompressibility. That is an important difference. Okay. Number two, I think viscosity is important in the experiments, but I don't think it will change things dramatically as long as you also have a friction, meaning as long as you have a viscous screening length, which is finite. Okay. Right. Now, if you don't have friction, well, then the system is generically unstable. And then I don't even know where to start, essentially, doing this kind of analysis. Okay. So, but the incompressibility, that's an important difference.
Right.
Okay. And it's got to be technical. So I wasn't going to get into that, but that's an important difference. And yes, you're absolutely right. The experiments have that.
Right. Okay. Thanks.
So another thing I wanted to say about the active torque, which I think is very interesting, if we just look at two defects, in this case, we're looking at 2 + 1F defects, and we ask what are the stable configurations when we have 2 collinear + 1F defects. What we will find stable to this, what I call the active torque, okay? What we will find is that for an extensile system, the stable configuration is the one shown here to the left, where they are head-to-head, if you like, okay? And for a contractile system, the stable one is the one shown here to the right, where they are tail-to-tail. Now, this one, from a far distance, will look like a vortex light +1 defect, while the one that is stable for the extensile system for a large distance looks like a +1 defect again, but in the shape of an aster. Now, interestingly enough, and this again is very qualitative, but to me is quite suggestive, going back to the experiments in Hydra by Kinner and Karen, what she sees is that as these organisms, so this is an organism where you start from a fragment and then it balls up, it makes a ball, and then it starts elongating, and then it starts making buds, and then the mouth and the tail and the foot and so on. So what she sees is that when the organism is still sort of in the shape of a ball, you do see plus or minus 1F, actually plus 1F defects. In this case, you must have a total topological charge of +2, so the minimum you can have is 4 plus 1F defects. You can have a few others balanced by minus 1F, but as time goes on, 2 plus 1F defects tend to come close, and they come close, they acquire precisely this configuration, and that is actually where the foot of the organism emerges. And this is interesting for a couple of reasons. Well, first of all, it looks like it's an example of a system where this kind of configuration is indeed stable. And she really seems able to distinguish between this configuration of 2 tightly bound +1F from a true +1, which is actually seen at the formation of the mouth of the organism. Secondly, again, this is a clear indication that the stresses in this system are again extensile, as in the Dojic microtubule system, although you're talking here about actin filaments, and so it wasn't necessarily clear that the stresses would be extensile as compared to contractile. So it's another example of a system where by looking at the defects, I think you can learn quite a bit about what's happening physically in the system. Okay, well, I'm almost done. I should be close to be done. So let me just tell you a couple of more interesting things. Now, going back again to, the equation for the orientation of the +1F defect and these aligning torques here. Now, this type of torque that says that the polar particle aligns not with the orientation with its neighbors as it's in the traditional V-check model, but with the force the particle feels due to the interaction with the neighbors, which of course depends on the orientation of the neighbors and on their position, is a type of alignment interaction that has been used to describe particles and even systems like cells, and is known to actually give flocking in this type of V-check type models. So then you could actually ask, well, can we then have flocking of these +1F defects? Can we have orientational order of these +1F defects? And we actually looked at these. We looked at these in a different way that I don't have time to go through by actually constructing sort of a hydrodynamic of the defect gas itself. But what we found is that indeed, in this system of where there is friction with the substrate, you can actually get a state where the defects are flocking in the sense that they are on average oriented in the same direction. They exhibit polar order. And this was actually, as you actually be seen in some simulations. These are older one by the group of Aparna Bhaskaran. I think actually Sumesh has seen this also. We have seen it in simulations. Is generally associated with the formation of this kind of structure in the nematic order, sometimes called kink walls, sometimes called arches by different people, which actually are also easy path of motion for the +1F defect and contribute to creating this kind of polar order. Another way to say is that the polar order of the defects is accompanied by some kind of a symmetric structure in the nematic order in the direction perpendicular that of polar order of the defects. And this happens whenever the nematic distortions relax more slowly than the defect reorientation. Essentially, the defects get trapped into these regions of high distortion. When the system is incompressible or there is no substrate, this type of order is not seen, and then the situation is really quite different. One thing we've been doing most recently is actually in collaboration with the student Farzan Bafa, Mark Bowick, and Boris Schreman here at KITP, is actually to try to go beyond this sort of single defect description and take into account the fact that actually defects really have long-range interactions, and so multi-defect interactions are important. And we have been able to obtain, again, the dynamical equations for the defect positions that include these many defect interactions and result in forces between the defects that are no longer central, like the Coulomb force, and often non-reciprocal, meaning the force that one defect A exerts on B is different from the one that B exerts on A. And one example of these kind of forces that come about where you consider more than a defect pair, essentially, is the following. If you look at two isolated +1F, they tend to align anti-parallel, like in this image over here. But if you put a third interstitial defect, is here, for instance, a -1F between the two +1F, then they actually tend to align parallel. And this is actually what happens in why we get the polar order state, because in the region between these rows of aligned +1F defects, we actually have -1F defects. And this has actually been seen in experiments by Alberto Fernandez Nieves in the microtubule bundles, you see here is an image of two plus 1F that are aligned anti-parallel. And here he has captured the situation where there is an interstitial plus 1F, sorry, interstitial minus 1F, and the two defects are now aligned parallel to each other. So this suggests again that these interactions seem to be starting to describe some of what is observed in experiments. Well, we have also used these continuum equations I alluded to, but I don't think I want to get into this, to actually describe the effect of how defects can be trapped by spatially inhomogeneous activity. And we are doing some more work on that, but I think it be time for me to conclude here. So what I've been trying to tell you is that defects can actually, in some sense, represent intrinsic probes of flow and mechanics in active system. And you can actually manipulate active flow by controlling and confining defects. So I showed you that we can describe defects as a mixture of active and passive particles, that we can think of active turbulence as an activity-driven Berezinski-Kosterlitz-Thouless transition. And we have some prediction for emergent states of defects that have been seen in simulations, but not necessarily in experiments. I haven't really told you about this, but we have constructed a hydrodynamic theory of the defect gas that actually can be used to describe situations with activity gradients, where activity gradients sort of act like an external electric field on defect charges and can provide a way for sorting defects and confining them. And the question that both Sriram and Sumesh raised of the role of hydrodynamic flows, and in particular the role of compressibility, is still something we are working on. It's still somewhat of an open question. So with that, I'd like to thank you, but I also want to thank and highlight the people that did a lot of this work. This is an image of my group here at UCSB before lockdown. So this is from last year. Now we only meet each other as we are now doing through Zoom on computer screens. The work on defects, as I said, was done, a lot of it was done by a former student, Suraj Shankar, in collaboration actually with Sriram and Mark Bowick. But many other people have contributed, that are continuing to contribute, especially the ones highlighted in blue. Collaborators from and former students from quite some time ago. And more recently, Luisa Angeluta Bauer, one of the few people who came here to KTP in spite of the pandemic, and Boris Schreiman. And currently, also two undergraduates, Supavita Pokamvit and Link Morgan, a student, Farzan Wafa, who is just finishing, and the postdoc, Ji Hong Yu. And I would like to go back again to this image of Aditi that I started with to highlight how a lot of this work, again, was really seeded and started by the beautiful work she did for her thesis on active pneumatic and active systems in general. So with that, again, I thank you, and I hope there are some more questions.
Yeah, I have a question I can ask.
Please go ahead.
Yeah, thank you. This is a fantastic talk. I enjoyed very much. My question is, in particulates, self-propelled particles, when you have equations governing their motion dynamics, how do you implement incompressibility? It's easy to visualize this in fluid models, but
no. When I have self-propelled particles, so the equations for the self-propelled particles are derived by starting with the hydrodynamic equations, and essentially the interactions and the self-propulsion are essentially how to say are a way of re-expressing the flow-induced distortions in terms of defect degrees of freedom. Okay, so the incompressibility will be enforced in the hydrodynamic equations and leads to changes in the equation of motion for the particles, but it doesn't appear, it's not that you impose it in the equation of motion for the particles. Another way to say, yeah, right. So, the cell propulsion, for instance, of the defects is simply arises from the fact that the defect is a distortion of pneumatic order. A distortion of pneumatic order generates a flow, and this flow at the defect core generates a cell propulsion. Incompressibility will modify these flows and therefore modifies possibly the cell propulsion. Actually, incompressibility decreases the cell propulsion of the defects. This we know, this we have looked at. Okay, but again, something that you impose at the level of hydrodynamics.
Okay, just one more question. There was a slide where you showed for the self-propulsion versus elasticity, where the region of turbulence was shrunk because of an appearance of an ordered phase. Right? You had a chaotic middle region.
Yes.
Is that a new turbulent region for the movement of particles?
If you're referring to these, right?
Not the next figure.
Next figure.
So here you have a turbulent region, and then there's a bound region. But in the next slide, you had shown that there's a middle region where the motion is chaotic.
Here you are saying. Well, so here, so here what I'm saying is that this is a prediction of us, so that has not been seen in experiments, I should say. Okay, what I'm saying is that, so here you have an homogeneous pneumatic, you increase activity, you go to this turbulent state, but eventually, and I should say, if you are on a substrate, here the presence of the substrate is important. If you are on a substrate, this turbulent state gives place to a state where the defects are themselves ordered. It's a state where the defects are all on the plus 1F are on average traveling in the same direction. And the pneumatic distortion has these modulations in the direction perpendicular to the one in which the defect travels. So there is a symmetric type phase gradient of the director, and there is polar order of the defects. So indeed, you go from what we call defect chaos to a state of defect order. And this has been seen in simulations of active pneumatics on a substrate.
Thank you.
Okay. So it's funny, it's like, activity first disorders and then it seems to induce order.
Yeah.
Order of the active defects, which are like active particles, and so themselves form these order states.
Thank you, Christina.
Okay.
Right. So, Christina, there are a few questions in the chat box. I can read them out for you one by one. The first question is from Sriram Ramaswamy. Why doesn't the argument about an interstitial minus half aligning
You are breaking up. I don't know if it's me or but I
yeah, so I was saying, yeah, why
so Sriram, you can speak, right?
Yeah, why doesn't the argument about an interstitial minus half aligning to plus half
you can ask
apply in equilibrium too? When the picture you drew seemed to just apply to the elastic distortions, and it looked like you could have the same argument applying in equilibrium. So I was wondering.
Yes, this has nothing to do with activity.
Okay.
Absolutely, I should have said that. Yes, absolutely. You're absolutely right. Yeah.
Okay, thanks.
It applies in equilibrium. This just has to do, after all, in equilibrium also, there are multi-defect interactions. The only thing is that in equilibrium, nobody has ever worried about the orientation of the defects because it didn't seem to matter, but it does.
Yeah, thanks.
Okay, I have something came up on my screen. It says, Ganapati Bhaskaran is requesting to annotate the share content. Oh, I see. He's asking me. Well, I don't know how to do this. So
Sorry.
I'm going to decline.
I think it was a mistake, Christine. I am very sorry. I enjoyed your talk. I was playing with the settings.
Okay,
but
thank you.
It's a good opportunity. If you hear me, I have a short question.
Okay.
In the context of layered superconductors, we found out a BKT state can be transformed into a what you call as ordered block state. So I will communicate with you. It's fascinating. I didn't realize all these new developments.
Okay. Okay.
The context of layered superconductors.
Sounds good. Thank you. Because actually, I think there should be a connection with that.
Yeah. Thank you very much.
Okay. So I don't know if people see this window, but I don't know how to get rid of it. Eventually, we'll do.
Okay, so question from Ryan Chatterjee. Ryan Chatterjee, are you here? Would you like to ask your question?
He's watching the online stream.
Can I read it out? Sunita, can I read it out?
Please read it out because Ryan is watching online stream.
Okay, great. So the question is, my question is 2018 PRL work. So are you saying that below a certain but non-zero activity order? Is the question clear?
I think so. Again, you're kind of very choppy. So I think you're asking me whether I'm saying that there is a finite activity below which one should have a nematic order. Is that the question?
Yes, I think that was the question. Do you observe stable order? That was the question.
That's what we are saying. Of course, only quasi long range order to be precise. But yes, that's what we are saying. This is something that has actually been debated whether or not they would say, but that's what we are saying. Yes.
So the next question is from Chaitanya. So the question is, effects can be used to extrude cells. Are there any ways to induce or create effects? If so, can that technique be used to extrude cancer tumor cells as an alternative to chemotherapy?
I don't quite get that. I'm sorry. It's really that. Okay, let me try something here. Maybe my microphone might be too loud. Okay, try say it again. There's something you were saying something about cell exclusions and cancer, but I don't get the question.
Christina,
can I explain the question? So thanks for the interesting talk, Christina. I have a question related to cell extrusion. So in one slide, you related the cell extrusion with defect at that location. So is there any way to induce a defect so that one can extrude a cancer cell? It's like an alternate to chemotherapy.
Oh, okay. I don't know. So it's the defect seems to be a region of accumulations of cell density, and that's why a cell gets extruded. I don't know how you would. I mean, I could imagine you could induce. Sure, you could induce a defect by patterning of the substrate, but that's only in vitro, obviously. So this has been done. You take cell monolayers, you put them on pattern substrate, and then you can actually induce defects. I think Francesca Serra at Johns Hopkins has been doing this. But in vivo, I don't know. I have no idea. Interesting question.
Thanks, Bruce.
Right. So there's a question from Rajesh Ganapati. Are you here? No problem. I can ask
online,
it. So
online. He's online.
If I see plus half defects in a dense assembly of polar active particles, is there a necessity for the velocities to be aligned near a plus half defect?
I guess I'm not quite understanding that. So the question is, if I have a plus 1f, if I think of a plus 1f defect as active particle, whether the velocity must be aligned or not.
No, Christina, what Rajesh is asking, Rajesh says if you see plus 1/2 defects in a
Yeah.
dense assembly of polar active particles, is
Yeah.
there a necessity for their velocities, that is the velocities of the polar active particles, to be aligned near a plus 1/2 defect? Of course, that means you need both a polar system and plus half defects, which might pose you some difficulties. I don't know.
Yeah, I don't know how to do that, because if I have a polar, I don't know how I would make a plus 1/2 defect in a polar system.
You could disperse polar active particles in an active nematic, perhaps.
Yes, it's true. I mean,
That might be a thing to think about.
maybe that may be something to think about. I mean, I don't know. I don't know the answer. I mean, in in these experiments of Oleg Lavrentovich, where they put bacteria in passive nematic, they certainly see an interaction of the bacteria, which you can think of the bacteria as polar particles, with the nematic defects and the nematic structure, but don't think they're ever dense enough to really worry about alignment of the polar particles, which are the bacteria again. So yeah, I don't know. I'm not sure that I have an answer to that, but it's an interesting thing. But I'm going to try to. I mean, I think it's quite interesting, the idea. In some sense, it's the idea of worrying about the interplay of polar and nematic order. Essentially, you have a system that can have what kind of interplay of the two type of order. That's actually an interesting thing to look at. We actually looked at something along those lines a very long time ago with Tanny Liverpool, but we didn't get very far at that time.
Thank you. So, a question from Shraddha Mishra. Shraddha, would you like to ask your question?
Yes. Hello, Priscilla. Yeah, hi. So I have a
Yeah.
like maybe it's a very simple thing. In this microscopic model of this plus minus half defect, so there is a like effective alignment of this plus half defect. But is there also segregation of defect like many plus half at one place, because it can lead to some higher order defect like you have shown, like plus one kind of or any other kind of, and maybe it can also lead to some higher order structures in the system.
So in what I call the state where the plus 1/2 flock, if you like,
yes,
there is some kind of a segregation in the sense that they do tend to separate. The minus 1/2 are like left behind in the grooves of these arches, if you like.
Okay.
Another way of separating plus and minus 1/2 defects is by using activity gradient. If you have a region where, say you pattern your system so that there is a active strip surrounded by passive regions, then there is a gradient of activity, which you can actually show creates like almost an electric field and can actually separate the defects. There'll be a strip of pluses and a strip of minuses on the two sides of the activity gradient. And people are starting to do this experimentally, actually, to try to separate or confine defects using activity gradients.
Okay. So my question was like, suppose this plus one, like what is the name? This made by this contractile structure where this plus one structure has formed, like circular rotating kind of thing.
Yeah.
So that can maybe it can lead to, like, it cannot not necessary that it is a homogeneous distribution of pneumatic rods, let's say, but instead of that, let's say the center is void of particle, at the periphery there might be the high density. Is it seen in the experiments, or I don't know, maybe in the simulation?
So
that will be also plus one structure.
Yeah. So when you have the 2 plus 1/2 in the extensile case, where the 2 plus 1/2 form like an aster because they are that case, the center is a region of high density. Okay.
Yeah. Okay.
When they form the vortex type in the contractile case, I'm actually not sure because I haven't looked at it, but I think perhaps in that case the center might be a region of low density, as a matter of fact.
Okay.
But strangely enough, I'm hesitating a bit because I think actually I would like Sriram's thought on this as well. I cannot think of a contractile active pneumatic.
Okay. Okay.
Sriram, can you think of a contractile active pneumatic?
Do you mean a physical realization or do you
Experimentally, yes.
yeah, I mean,
I don't think.
For me, I'm always confused with contractile and extensile, so I can't think more. Yeah.
so supposing you took a bunch of these swimming algae and I don't know, craft.
No. But what I mean is that, as far as I know, every system where every active system in which pneumatic order has been seen, even ones where one expected to be contractile, they seem to be extensile.
Okay. Yeah,
Right.
mathematically it is possible.
That's what I'm saying. Well, actually, no, that's not quite true. There are some cellular systems in which one has seen contractile behavior, but the vast majority, yeah. Anyway,
The tendency might be related to what Sumesh and company have remarked, that if you had a collection of particles which at equilibrium had no particular inclination to go pneumatic, then extensility can push it over the edge and make it pneumatic because it can self-reinforce alignment, right?
Yeah, that may be, but I was just trying, yeah.
It's probably harder to find contractile ones, at least.
I cannot, that's right, exactly.
So this experiments from Benoit in France, I think they recently have shown that if you do not have cell-cell interactions in epithelial cells, then it...
Right, that's what I was thinking, yes.
Yeah,
Yeah.
contractile systems.
You're right. Yes, now I remember. I know there was something in the back of my mind. Yeah.
Okay, thank you.
So there is a question from Samir. I'll read out the question. Can flocking of defects be sustained as defects of opposite charge attracts?
Repeat the question, please.
Yeah. I'm sorry, actually there is a lot of rain going on outside. So
yeah, no, I know. That's why I'm having a hard time.
Defects of opposite charge attracts. How can you sustain the flocking of defects? That was the question. Samir, if you are here, you can also elaborate on.
I don't think so. The idea here is that because the +1F are motile, if they're oriented, they are attracted by the -1F, but if the activity is large enough, they can actually also move away and overcome the attraction, essentially. So, and you can kind of estimate when that will happen by balancing the propulsive force against the Coulomb interaction. You can estimate that. So that's the whole point. These defects, sometimes they look like they're repelling each other, even though, and you can see that in the movies of Zlomir Dojic, they look like they're repelling each other because if the activity is large enough for the right orientation, the propulsion can overcome the attraction. And so they're not really that they are repelling each other, but they're moving away fast enough that they can overcome the attraction.
Thank you so much. So we have a couple of minutes left in this session, so maybe one or two quick questions can be asked, if anybody would like to from the audience.
Manoj, I have a short question.
Please.
Christina, my colleagues talk about in colloids, equal charges attracting and so on in equilibrium situation. Is there any similarity to what you are talking about in non-equilibrium situation?
So, no, I heard it. You're saying, well, these are is a non-equilibrium situation in the sense of these propulsion. So these, if you want to think of these as particles, charges, yes, they're like opposite charges that attract themselves. But one of them, it's an active particle. It's a particle that generates its own motion, so it can run away. And if it runs away, if it runs away strongly enough, it will no longer. It can overcome the attraction of the other one. mean, if you go back and look at the movies from, let's see. Do you see my screen or do you see a window on top of it? I have a window on top of my screen that I don't know how to get rid of. I'm gonna try to go back to some place. I don't know where I was. Here. Okay. You see this? I think I need to go back further. Doesn't seem to be running. Okay. I don't know if you can see this movie. I have a window on top of it.
Yeah,
so
I can see. Yeah.
But there are arrows pointing to two defects, right? At some point of the movie, a blue arrow pointing to, I think, the -1F, and the red arrow pointing to the +1F. And you can see that the +1F is running away. It's not that they're not attracted to each other, but it's like running away because there's an activity that it drives it away faster than the attraction, essentially.
Thank you. Thank you.
Sure. How do I get rid of this window? Who knows?
Thank you.
Ganapati, I think you need to remove a window that I don't know how to do it. I have some
Any questions from the audience? Okay, I don't hear any more questions. I don't see anything in the chat box either. I hope I have addressed all the questions in the chat box. I hope so. Yes, I believe so. All right.
Okay.
All right. So
There are no further questions from here online also. I just checked.
all right. Yeah, please. Thank you,
No, it's
Sunetra.
fine. Yeah.
All right. Thank you, Sunetra. So let us thank Professor Marchetti for a really fascinating talk. Thank you so much.
Well, thank you all, and thank you very much for the nice questions. I am not sure that I will stay through the end because I still have to have dinner, among other things. I made my husband wait for dinner. But are you posting these talks online, or are you planning to do that, or not? No.
Yes, we are recording it, so we will certainly post this.
Okay, so maybe I'll look at the talks later on. So
Sure, absolutely.
then,
Thank you.
okay. Thank you very much. I'll stay a little bit now. Do I need to unshare my screen, right? What am I doing? How do I do that?
See the orange thing on top, which would allow you to unshare.
Okay. Yes, I got it. Okay, got it. I'm out.
Okay, I thank you so much. I would now like to welcome my colleague, Dr. Dilip Sapni, to chair the next session. Dilip?
Yes. Hello? Am I audible?
Yes, Dilip, you are audible.
Yes. Thank you, Manoj. I would like to invite Professor Guruswamy Kumaraswamy. He's a professor at Department of Chemical Engineering, IIT Bombay. And his work focuses on controlling the structure and investigating structure-property relations in soft matter systems. These systems range from polymers to surfactants, lipids to colloids. He collaborates extensively with industry in area of polymers, healthcare, personal care, and waste valorization, etc. A little more about him. He received his BTech degree from Chemical Engineering, IIT Bombay in 1994. He then obtained an MSc degree and PhD in Chemical Engineering from California Institute of Technology. After that, he spent a year as a postdoctoral fellow at Max Planck Institute for Colloids and Interfaces in Germany. And after finishing his postdoc, he joined Polymer Science and Engineering Division at the CSIR National Chemical Laboratory in Pune. And after that, he moved to IIT Bombay and presently a professor at Chemical Engineering, IIT Bombay. He got numerous recognition for his work, which includes CSIR Young Scientist Award and NCL Scientist of the Year Award. He is also a fellow of the American Physical Society and INAE. Without taking much time, I would like to invite Professor Guruswamy to deliver his talk. It's on self-assembled colloids from filaments to 3D sponges. Over to you, Guru.
Thank you, Dilip. Just to check, can you hear me?
Yes, perfect. I can hear you.
Perfect, great. And you can see my slides.
Yes, we can.
Wonderful. Okay, so thank you very much for the invitation to give a talk. I'm honored to speak in the memory of Aditi. I'll tell you a little bit about my connection with her. But before I do that, let me tell you a little bit about what I'm going to say today. My work has focused on, amongst other things, looking at colloids, and I'm going to talk about colloids, and I'm going to tell you 3 short stories. Right. The second story is a story about active colloids that are strung together to form necklace-like objects. And that is work that we did some years ago. The first and the last story are about passive Brownian objects, right? And so in a sense, one would imagine that they're far more boring than the really beautiful nematics that Christina showed in the last talk. But I hope to convince you that there's a lot of interesting things in Brownian systems as well, without even getting into active systems. So most of the work that I'll tell you about is from the PhD thesis of Bipul Biswas. Bipul's a physicist and is currently a postdoc at the University of Massachusetts with Manasa. And the last story I'll tell is you know, the fact that I'm from an engineering department. I need to speak a little bit about technology, and I'll tell you a little bit about the work that came from the thesis of Karthika, who's now a postdoc in Minnesota, and Soumyajyoti, who works at a startup company in Hyderabad, about technology that can come from harnessing some of these self-assembly techniques. Several collaborators whose work I'll allude to during the talk. Suresh Bhatt at NCL, with whom I did some of the confocal microscopy experiments. Apratim at IISER Pune, whose work I will not talk about, which discusses simulations of some of these Brownian systems. Arindam at IIT Bombay, with whom I've done some particle tracking microscopy, and Sanat Kumar at Columbia, who's been a collaborator for many years. So Dilip mentioned that I graduated from IIT Bombay in '94, which means it was my 25th anniversary of graduating from IIT Bombay last year. Together to talk about all the fun times we had as undergraduates. When we joined IIT Bombay, there were about 300 of us, and only a very small fraction, about 9 of us were women. Unfortunately, in those times, there were fewer women who joined the Indian Institutes of Technology. And so this is a picture of the 9 lovely women who were part of my class. Some of you will recognize Shachi, who is Madan's colleague at NCPS. And this person over to the left here is Aditi Simha. I did not know Aditi very well, but we did do a lab together. So Aditi and I were in the same lab class in 1990 when she joined IIT Bombay. But after a year at IIT Bombay, she left to go back and do some real physics, and she moved back to Bangalore, and then launched into some very exquisite physics, initially starting with work that she did with Sriram at IISc during her PhD. So in that sense, given that Aditi was actually a classmate of mine, it's especially a privilege for me to be able to speak at the symposium. So I thank the organizers for inviting me to speak here. And this is a picture that I'm guessing some of you probably have not seen from Aditi's undergraduate days before, when she was at IIT Bombay. So Aditi's physics, and Christina has again spoken about that, talks about beautiful flocking behavior, about the hydrodynamics of collective systems. So, for example, things like bird flocks or swarms of fish, where a lot of the interest really comes from the fact that you're talking about systems where there are interactions that are collective systems where each of these entities in the system interact with each other. Think about today talks about interaction in a different sense. Right? So I don't have systems where I have higher density globally, local density. That comes from systems where there are bonded interactions and connectivity. So think, for example, of systems where you have these units that are connected in some manner to each other. So our inspiration for this work really comes from looking at polymers, right? And if you think about a polymer is many mers connected together. So these are long covalently connected objects. And in a sense, the connectivity defines the polymerness of these materials, right? And so here's a beautiful image from Wikipedia of how long these polymeric strands can be. This is a common polymer, polyethylene, right? And one of the things that's really quite remarkable about these polymers is the universality that we see in the properties that comes purely from the fact that they're connected objects. And so, for example, if I look at a series of this old data from the literature, if I look at a series of different polymers, right? So it's polystyrene, polyvinyl acetate, polyethylene glycol, so a variety of different chemistries. These are long polymers and they're flexible, right? And when you take these systems, what you see is that the viscosity initially increases linearly with the molecular weight, right? And then beyond a certain critical molecular weight, it goes up as a power law. It goes up as a 3.4 power of the molecular weight in these systems, right? And this is what's remarkable is that these are very, very different chemistries in these polymers, and yet you see the same universal behavior. And so, in a sense, polymer-like behavior is really a rather than specifically of the chemistry. The chemistry puts in the details, and those are very interesting and important as well. But a lot of these physical properties can really be understood on the basis of connectivity, right? And so my talk today will probe the effect of connectivity. Okay, so I was told again that there would be a lot of undergraduates, and so I thought one of the things that could emphasize what would happen with connectivity is very easily shown with some very beautiful videos. So here is water, right? And you take water and you stir it, and you see that this meniscus forms because of a balance between centrifugal force and gravity. And then into this polymer, you dissolve this polymer. Into this water, you dissolve this water-soluble polymer. It's a high molecular weight polymer, and you notice that's a relatively small volume of it. And what you notice is that as the polymer dissolves to form a polymeric solution, again, it's a dilute polymer solution, you see a complete reversal of this meniscus, and it sort of flips over to form this what's called a Weisenberg effect or a rod climbing effect. Really comes from the elasticity in these systems. That's a function of the connectivity. These are videos, by the way, taken from the Wales Institute of Non-Newtonian Fluid Mechanics. I've given you YouTube links where you can see these. There's amazing exhibit. So here's another very, very intriguing phenomenon. And this is something you won't see with water, right? So really connectivity induces or gives rise to physical properties that are very, very different from what we think about for small molecules. So what we set out to do is to sort of inspired by polymers. Now, polymers are molecular objects, right? And so when you work with polymers, it is very difficult to go back and probe these polymers by visualizing what each polymer molecule does. There's been some outstanding experiments that Steve Chu really initiated where you can start visualizing DNA, but those are very limited, very difficult experiments. So what we set out to do was, inspired by these polymers, to ask the question if we could create systems where we could take colloids and connect them together, right? And why colloids? Well, because two things really. One is that these are objects that are small enough that you can look at objects that are Brownian, and so where thermal fluctuations still play an important role, and yet these are sufficiently large and therefore also sufficiently slow that you could use very simple techniques, optical microscopy, to look at these systems, right? So these are then amenable to very simple tabletop experiments, and that's really, I think, the joy of doing soft matter physics, right? So for example, if I take a 1 micron colloid in water at room temperature and I watch it diffusing around, you get a diffusivity that's of the order of about 0.2 microns squared per second, which means that it diffuses about a micron over 10 seconds. These are length and time scales that are very amenable to simple experimentation. And therefore, it's not a surprise that these kinds of systems have been adopted by the community starting many years ago. And people have done experiments. They've looked at, for example, phenomena trying to mimic atomic systems using colloidal systems, and there are limitations to where you can go there. But really looking at, for example, would classical nucleation theory hold when you look at crystallization of these colloids to form these structures? And you can again image these and visualize each one of these. More recent work that's come out of the group of Rajesh Ganapathy at JNC shows some very, very beautiful examples of what one can do to visualize, for example, motion at crystal grain boundaries, look at glassy dynamics, again, using these kinds of colloidal systems. And one other work which I absolutely loved when it first came out from the group of Henk Lekkerkerker was the fact that you could now tailor these materials such that you could start looking at directly imaging thermal capillary waves using colloidal fluid, a colloidal condensed phase in equilibrium with a colloidal gas. And this is work that came out several years ago, but extremely pretty work, right? I spent many years at the National Chemical Laboratory, and one of the things that absolutely astounded me was the kind of advances that have been made in colloid chemistry that now allows us to produce almost any kind of colloid that we'd like at will, right? You can produce colloids with perfectly well-defined size distributions, monodisperse colloids. I'll speak a little bit about Janus colloids, right? Where you have colloids which have two very different functionalities on two halves. And this is something that at IIT Madras, the chemical engineering group of Basavraj and IDEA have been doing with great success. And not only can one tailor the chemistry of these colloids, but this tailoring the chemistry also then allows us to control and really customize it to at will, right? So you can control the electrostatic interactions, of course, but people have now shown that you can graft DNA strands on these colloidal surfaces such that you can really tune the nature and the length scale over which these colloids interact. And so there's been really amazing advances in the synthetic capabilities that allow us to work with these colloids. The other really enabling technology has been the adoption from our colleagues in biology of imaging tools, especially confocal laser scanning microscopy. And this is again something that people like Rajesh have put to good use when they've looked at visualizing structure formation in these materials. So you could, in addition to other kinds of chemistry, make these colloids fluorescent and then very, very accurately track the center of mass of each of these colloids using tools like confocal laser scanning microscopy, especially with fast scan heads. There's quite a lot that one can do. And these are, in my opinion, two of the reasons why this field has really taken off, because you really now have access to model systems where you can manipulate the systems at will and create exactly the kind of model systems that you need for your experiments. So the question that we asked starting a few years ago was, if I were to be inspired by polymers, how would I take these colloids and link them up, right? Because I can make these colloids, but then if I want to make a string of colloids, control that string, how does one line these colloids up and link them together? And so something that had been taught to us first by the group of Alice Gast, I believe this is the first, and I've seen examples of this. This is work that was done by Eric First when he was a PhD student with Alice Gast a long time ago now, was that if you could take these colloids and you put them in an AC field, then the this standard dielectrophoresis, you induce dipolar interactions, and if you have a high enough frequency for the electric field, you don't have counterions being moved around by the field, and so you can get these colloids to then line up to form these beautiful string-like objects, right? And again, many years ago, Anand Yetiraj, when he was a postdoc with Van Bladeren, came up with a very nice phase diagram for the behavior of these materials as a function of the electric field in these systems, right? So the experimental system is very simple. You buy these colloids off the shelf, you take a dispersion of them, put them in electric field, and then line them up. What Hanumantha Vutukuri and Van Plateren did, and also what Eric First and Alice Gass did, is to work with polymeric colloids, and they would line them up in a field and then heat the entire system to a temperature where the polymers will essentially fuse together, right? And when you do that, you can get these relatively stiff strings of colloids where the edges are essentially fused together to form these string-like objects. So we decided to, at the first instance, adopt this methodology in terms of lining up the colloids, but use a different chemistry to link them together. So let me briefly tell you about the system that we put together. So this system here, and so this is the first question I'm going to talk to you about, which is a Brownian passive system. And I'm going to talk to you about what happens if I take these colloidal necklaces and you put them in a bad solvent. Okay, and so let me tell you what I mean by each of these terms. Right? So how do I make a colloidal necklace? What do I mean by a bad solvent? And how do I make this experiment happen? So my experimental system, and this is the monomeric bead, which I'm going to string together to form the necklace. This monomeric bead comprises of a 1 micron polystyrene colloid. The colloid itself is anionic, which means it has a negative charge. The zeta potential is negative, and I buy this. And to that, I add a microgel particle of a polymer called polynipam, poly-N-isopropyl-lacrylamide. This is the polymeric structure for those who are interested. It's actually not exactly this polymer, but I also have I co-polymerize it with some amine groups that give it a cationic functionality. So that means that this microgel system, which is this small particle that I make about 100 nanometers in size, so much smaller than the colloid, is a positively charged hydrogel particle. Very little polymer, lots of water around it, but it's positively charged, and it has this polynipam, right? Now, what's special about polynipam is the fact that this is what I call a LCST, or lower critical solution temperature polymer, which means that polynipam is water soluble because of the fact that you can have water molecules that associate with these, with for example, things like the carboxyl group and the amide group. But because you have hydrophobic groups that are linked to it, as you go to high temperature, the water molecules gain translation entropy by separating from this, which means the polymer becomes insoluble in water, right? And so, for example, you have a microgel particle which is at about 25 Celsius, swollen because water is a good solvent, it swells in that polymer. But as you heat it up above, let's say about 35 Celsius or so, it shrinks because the water is expelled from these systems and it becomes a hydrophobic particle, right? And if you do this at high enough concentrations, these particles will actually start aggregating to form a big lump. And so by taking polynipam microgels, you can essentially create a system where you can change the solvophilicity by changing temperature. So at low temperatures, this is a system that likes the solvent, and at high temperatures, this becomes a hydrophobic material, or it hates the solvent. In this case, the solvent is water. So I take these microgel particles, and since these are cationic, they absorb on the surface of this anionic polystyrene colloid, and these are too small to see, right? They're 100 nanometer particles. So what I see is really the polystyrene colloid. Okay, and if I pick fluorescent polystyrene, where I start off at 25 Celsius, I can see these individual micron-sized polystyrene colloids, and then once I heat it up above the LCST, these colloids, because the surfaces are now covered with this polymer and the polymer hates the solvent, it induces colloid-colloid attraction to then give you these kinds of aggregate structures. And this is reversible. So if I cool it back down, they will essentially separate from each other and go back to forming these individual micron-sized colloidal particles that are stabilized by the charge repulsions between these particles, right? So that is the monomeric system. The point I made is that there is an amine group that allows you to get a cationic charge, but it also then allows you to cross-link these systems, right? So what we do is we take these systems, and like what was done by people like Gast and Van Plateren, you line them up in an electric field, and then once it's lined up in the field, you put in a cross-linker that allows you to chemically cross-link these microgel particles, right? So the colloids are covered by microgel. So it's like a it's like a wire mesh of microgels that's cross-linked and then cross-linked across from the colloids to form these string-like particles, right? So these springs are essentially the connection between these polystyrene colloids induced by the cross-linking of these microgel particles, right? And so that's the system that we come up with. Very easy to implement, and one can actually control this bond stiffness or the bond rigidity, as well as the torsional rigidity of these systems, simply by varying the cross-linking time. I gave you some data just to show you that we can characterize this, looking at the distribution of these bond lengths as these rattle around because of thermal forces, and similarly we can measure bond angles and look at the distribution of bond angles, and from that characterize the bond rigidity in these systems, as well as the torsional rigidity in these systems.
Guru, I have a question. Sriram here. How do you, is it at all tricky to make sure that they form one-dimensional aggregates and don't get branched and don't, I mean, is the field enough to do that? And is that all it takes or what?
Right. So again, one of the things we can learn from is the phase diagram that Anand Yetiraj did as part of his postdoc work, right? So if you have the right concentrations and the right fields, you really simply get one-dimensional aggregates, and it's almost exclusively that you get one-dimensional aggregates. As you vary the fields, as I recall, you don't really get branches, but you can get these strings to at some point start attracting each other and then form sheet-like structures, as well as three-dimensional structures as you go to higher fields or higher concentrations, right? So the phase diagram for these systems in the presence of a field is mapped out, and we can simply use that to ensure that we get essentially 1D structures in these systems. Does that address your question? Sure.
Yeah, thanks.
Okay, so once we make these systems, you can essentially okay, how do I lose my point? My video, unless I lose my pointer. 1 second. Apologize for this. Right. So once you make these systems, you can then just simply look at them under simple optical microscopy. And here's a semi-flexible polymer. You can see these beads that are put together that are wiggling around. And what you can do is then look at the variation in the end-to-end distance as a function of time. And what you see is that there are polymers that you can make that are relatively rigid. And so I define then this flexibility parameter. And the smaller flexibility parameter tells me that I have smaller excursions in the end-to-end distance, while the more flexible systems have larger excursions. So larger is this flexibility parameter, larger is the flexibility of these systems, right? And so these flexibility parameters also correlate with the bond stiffness, and therefore correlates with the amount of cross-linking that we have in the system. So that's sort of an experimental handle that we can exploit to control the flexibility in these systems, right? So we make these systems, and what we then do is, once we've made these systems, now the necklace by itself is thermoresponsive, in that as you heat up these necklaces, effectively you get higher monomer-monomer interactions, and the monomer here are these colloidal beads. And so you have monomer-monomer interactions that become more favorable than the monomer-solvent interactions, and therefore this necklace now is a necklace in a bad solvent as you go to higher temperature. And if you plot then the end-to-end distance normalized by the end-to-end distance at low temperature, what you can see is that there is, as you go to high temperature, a decrease in the end-to-end distance of these polymers as you go to high temperature. So when I say polymers here, I mean, in this case, the colloidal polymers in the systems. And this is kind of intuitive, it makes sense. And what you can see is that if you have systems that are relatively rigid, this is a parameter, that's a flexibility parameter of 10 to the minus 5, you have a smaller decrease in the end-to-end distance. It's about 10%. This is about what you would expect if the microgel particles contracted. And much larger decreases as you go to more flexible systems. In this case, the flexibility parameter is significantly higher than you had for the case of the black squares, right? And so we can then look at things like the local density in this coil state, where you plot the density as a ratio of the number of particles by the cube of the end-to-end distance. And what you can see is that for flexible chains like you have here, these flexible chains show you a much higher increase in the density inside this coil as you go to high temperatures compared to the relatively stiff or the rigid materials, right? And so this is not something which is particularly surprising, but it's a very, very nice demonstration of what we can see in this. What's really interesting, in my opinion, is this, right? So we are looking now at data for semi-flexible necklaces, right? So here you have a chi parameter in a certain range. We'll look at this here, and let's watch this. There's some drift in this because of the thermal gradients in the system as you heat it up. But as you heat up this semi-flexible system and you go to higher temperatures, what you'll see is that starting at about 35 Celsius or so, you get this system that shrinks, but also you start seeing this transition to something that looks like a helix, right? You see this variation. This is again normal optical microscopy, so you see the variation in the intensity as you go across the system. And so let me play this again. As you heat it up, there's a little bit of drift, but if you follow this particular chain, you can see that as you go above the point where you have the low critical solution temperature, this chain seems to sort of sense and coil to form these helical structures, right? And you can see these as well, multiple chains, though these are sort of less clear in these systems. Okay, and so you can see that these are helices because of the fact that you have this intensity variation, and as these chains rotate around, you can see that these are helices. When you have a two-dimensional view of these systems, it's not very easy to make sure that these are helices, but we've done these experiments a number of times, watch these things rotate in the field of view, and we're reasonably certain that these are helical structures. So what we see really is the following, right? So if you have very stiff systems, then as you heat these up, the rigid systems stay like rigid filament-like or rod-like systems, and there's a small shrinkage of about 10% or so. When you have much more flexible systems, then what you see is sometimes the formation of these kink-like structures, not very often, but occasionally, but more the formation of these aggregate-like structures where the flexible systems collapse to form relatively dense structures with the high local densities. And the really interesting thing, in our opinion, is sort of this intermediate scale of rigidity, where you start seeing the formation of these helical structures, right? We only see it at these intermediate stiffnesses, and these are helices that sort of form, and then they unfold, and then they refold again. There is no preferred handedness in these systems. You can find roughly an equal number of left and right-handed helices in these systems. So that really perplexed us, right? Because everything that we've learned from biology is that you need to have specific interactions to form helices, right? So if you think about peptides or DNA or any of these other biological systems, helix formation is driven by very specific directional hydrogen bonding interactions, right? You also see this in systems where you don't have hydrogen bonding. For example, in a lot of vinyl polymers, you have to have the stereochemistry in these systems that allows you to fold to form these kinds of helical systems. So there is interactions that give rise to helicity in these systems that come from the fact that you don't have purely symmetric systems. More recently, in colloidal systems, people have been able to induce the formation of chiral clusters, and this is really driven by forcing these colloids to aggregate under situations where you have steric constraints. So for example, you might have a larger colloid that's tied to a smaller colloid. These colloids are forced to aggregate maybe under the presence of magnetics. And then you have these systems that are these helical structures, or design specific interactions similar to what you see in biology. You can have DNA tethers that force these colloids to interact in a manner such that you have these very, very specific interactions that give you these colloidal architectures. So systems such as ours, where you really have no specific interactions, no directionality, you only have hydrogen bonding in these systems, the formation of these kinds of helical structures was very, very surprising to us.
Guru, I had a question. Sorry, I mean, if you just pour a viscous liquid, you pour honey or something, then you do get spontaneous twisting of either kind, right? I mean, it's not that shocking, is it? I mean, in that sense.
So those are the when you take honey and you pour it and you get twisting. Those are really hydrodynamically driven, right? I mean, these are systems that I'm not sure I see the analogy.
Even when you drop a rope, it'll coil, right? So isn't there just that kind of mechanics going on here, or is it not?
So when you so those are systems where you are imposing a steric constraint in a sense, right? So if you pour a rope, in a sense, what you're doing, and this is work that has been done by groups such as Banavar, is if you take a cylindrical structure and you confine it in some manner, right? If you confine it into a cylinder, then you can force it to form a helix, right? I'm not sure that analogy holds exactly here, but maybe we can talk about this. Maybe you can tell me why you feel that analogy holds here. But
okay,
similar to that, right? Similar.
So, Guru,
yes,
this is Madan here. I thought this had to do with the gain in the entropy of the particles. That the helical formation is driven by a gain in the entropy of the particles. Isn't that correct?
Right. So in this system, I'm not sure if that is the case, but let me just talk through that. So there's this work, and I think Madan, you pointed me to this, which is this entropically driven helix formation that was reported again some years ago, which talked about the fact that, right, and I subject it to depletion interactions, then you get this collapse of and that forms these kinds of helical interactions. So these are again helical structures that form in starting from a cylindrical segment and driven entirely by this entropic interactions that force these things to collapse. To a large extent, in this case, it's determined by the cylindrical the cylindrical nature of these segments, right? I mean, if you look at the analysis that they present, it's really driven by the cylindrical nature that you get in these segments. It's possible that a similar kind of situation might hold for particles that are jointed together, but I haven't yet seen an analysis of things like that. So a similar thing is when people talk about collapse of things like DNA, right? And so people have so this is work from Matteo Pasquale and Fred McIntosh that who've spoken about poor solvent in which you put a semi-flexible polymer, and the motivation is really come from the formation of these structures in biology. And what they've shown is the formation of what they call these racket-like structures, which eventually go to this equilibrium state, which is a toroid, right? But the formation of these kinds of helical structures at this intermediate level of flexibility, I think, is still something which there isn't a convincing explanation for. So my colleague at ICER Pune, Apratim, has been doing some simulations, but I won't talk about that. But the main takeaway from those simulations is that it seems to be an interplay of the kind of connectivity that we have in these systems, where you have these rigid colloids, right? So the difference here is you have this sort of uniform mechanical structure that you have in these cylindrical structures, as opposed to what we have here, which you have rigid colloids that are connected flexibly to form these necklace-like structures. So what Apratim thinks is it's that you have this collapse. In that sense, the collapse seems to be similar to this kind of a depletion interaction that you're seeing in these systems. But it really seems that this interplay of connectivity, rigidity, and collapse seems to give rise to these structures. I mean, my sort of naive way of thinking about it is, if you have a system that seeks to collapse and you have a flexible system, it collapses to form this coil. And we know this from flexible polymeric systems. And again, if you have a rod-like system, then as you go to a batch solvent, there's not much you can do because the rigidity is very high, and at best you can have rod aggregation at high concentrations. But it seems to be sort of this magical level of flexibility where you have this balance between the the force that drives the collapse and the flexibility, the semi-flexibility of the system that gives rise to the formation of these helical structures, right? So it's sort of a hand-waving explanation for now, and I don't know if that addresses your question, Madan. Right? So what we have is colloidal necklaces. There's no chiral motifs to start off with in these colloidal necklaces, but when you have this collapse, you form these helices with equal probability of right and left-handed helices. The helix formation that we see here is dynamic, so you see formation and unraveling of these helices. The fraction of helices goes up as you go to higher temperatures when the solvent becomes more more of a bad solvent. And I think, as compared to what people have shown in the past, and certainly there's no experimental demonstration of this as yet, people have looked at cylindrical filaments and not so much necklace of beads. This being an exception, that they've looked at toroid formation in these systems. And at least at the outset, looking at upper theme simulations, it seems to really come from some kind of an interplay of connectivity, rigidity, and collapse in these structures. Okay. So I can stop here. This is the end of my first segment and take questions, or I can move on to the next segment.
Guru, I have an elementary question. Just when you have the two particles connected, the connection points are actually anchored in the polymer mesh around them. They're not, that is, if I have two spheres like this, the contact points can't move around on the sphere, right?
Contact points. Okay. So let me put it this way. So the microgels are adsorbed physically on the polymer, so they are not cross-linked to the polymer. So they form like this rigid mesh. So think of it this way. If you go to these grocery stores and they give you those wire mesh bags, and you put a bunch of tomatoes in there, and the wire mesh bag is just that size, and then you twist around each tomato the wire mesh, right? So in principle, you can move, but it's very, very difficult for that point of contact to move. It's flexible, and in principle, the tomato can rotate inside that wire mesh structure, but that point of contact really cannot move around much on the mesh. So we let that happen in the simulations, and that also shows helical structures under some circumstances. But in the experiments, that's not the realization that I think we had.
Great, that's a very clear answer. Thank you.
Okay.
Can I ask a question, Vani here?
Yes,
Hi.
Please go ahead.
I just wanted to know what is the role of temperature here, in the sense that is its role only to make the solvent more bad, or can the similar structures can be realized if you vary the solvent condition at much lower temperatures? Can you still get this? Is there a specific role played by temperature other than inducing bad solvent condition?
Right. To the best of my knowledge, it is only that it makes a solvent bad. I don't anticipate. I mean, so if I could make the solvent bad at lower temperature by, for example, replacing the water with something else, it will possibly do the same thing. I need to think about how to do that exactly and how to experimentally do that, because inside the system, I inject another fluid. That's kind of difficult to do without perturbing the system. In my mind, it is really just that the solvent becomes bad as you go to higher temperature. That's about it.
Okay, and just a very quick follow-up question is, do you think this is something very specific to colloidal system, in the sense that about the size? But if you had polymers which are much smaller in size, monomers much smaller in size for regular, do you think these things will emerge there in those systems as well, or is this something specific to the colloid monomer sizes?
So I hesitate to make a molecular analogy to this system. The length over which these interactions exist are very different in the colloidal systems as compared to the molecular systems. If you take a molecular systems like polypropylene, right, these are completely apolar. There should be no specific interactions, but there are indeed van der Waals interactions that become very important when you get these things to twist, and that induces attractive interactions.
Okay.
So in that analogy to real molecular polymer systems is difficult. I saw there was a message from Rajesh in the chat, but it kind of disappeared. So could someone read it out to me?
Yeah. Hi, Guru.
Thanks.
So Rajesh has a question. He says that, have you attempted in bringing patchiness in the polystyrene particles to control the branching and also realize block copolymers of colloids? Is the question.
Not
Have you
yet.
tried the patchiness?
Very good question. And no, not yet. So patchiness, so we could induce branching by looking at patchiness, and that's true. So we could have very strong attractions and therefore induce branching in these systems, but we've never really looked at branch systems. Neither have we looked at as yet block-copolymer kind of structures where you have two kinds of strings that are joined to each other. So Van Bladren's group has realized some of these structures, but not using the kind of cross-linking chemistry that allows us this flexibility. But we haven't yet done that. Thanks, Rajesh. That's a very good question.
Guru, I have a question. Can you please comment on the critical length of these colloidal polymers on seeing these helices? Is there a critical length? Or
Absolutely. Yeah. So if you go back and look at the structures, we see structures where the helix pitch typically varies between 6 and 12 monomers, right? So you really need to have a colloid. You need to have 15 or more colloids that are linked together before you start seeing these helices. If they're very, very short, then you really don't have the opportunity to twist. There are other kinds of structures that might form. So this is only possible when your strings are long enough. So they have to be at least 15. These are typically 30 plus colloids that are linked together in the examples that I showed. Yeah, thank you very much. That's a good point which I should have mentioned.
Basa, can you please go ahead? Basa has a question. Please go ahead.
Hey Guru, really nice talk. So this, if you see, you used PNIPAM as a model system to really, adsorb onto polystyrene and cross-link them. But it turns out that the size of the particle, PNIPAM itself is about 100 nanometers compared to 1 micrometer of, spherical colloids. Of course, it gives you a flexibility of, working with temperature and, realizing the, but do you think more smaller, PNIPAM or even a molecular polymer, like, for example, you could have put PEI and cross-linked, right? Would such a system offer any advantage over the system that you're choosing?
Okay, the challenge would be to make it thermoresponsive. But that's a good point for me to transition to my next part, which is using polyethylenamine to cross-link these systems. So let me address that in just a minute. So you can also do that. So my second part is really a tribute to some of the work that Aditi did on active systems. And we looked at active systems in slightly different ways, right? So a lot of the work that Aditi's work focused on was to look at self-propelled colloids and looking at active colloids. And very often you get these self-propelled colloids by breaking symmetry, by creating what are called Janus particles, right? So you've got the Greek god Janus with two faces, and similarly you can create particles using a variety of chemistries. And Basa is an expert on some of these, where you have very different functionalities on both the sides of this particle, right? And then you can subsequently induce activity by either looking at interactions with fields. Steve Granick, Dennis Bartolo, Raman have talked about some of these things as well. Or the first systems that were introduced were really from Ayushman Sen's group at Penn State, which looked at running chemical reactions on one half of these and therefore inducing a non-equilibrium nature to these systems. But I'm going to focus on a very different realization that was suggested, I think, first by the group at IIT Madras, Sunil Kumar and Rona Joy, who was then at Math Science, to look at Brownian chains, right, where you have activity in these systems, but you don't necessarily have the symmetry breaking that comes from having a Janus particle. Rather, you have symmetry breaking from Brownian fluctuations in these systems, right? So what they developed was a model for a semi-flexible bead spring system. It's a self-avoiding chain. You've got active elements along the chain, and because you don't have any net force or torque on the system, you model the activity through these stresslet terms, right? And then you have a Brownian noise term that allows you to get these things to wiggle around in these systems. So you use the normal Oseen tensor for hydrodynamic interactions that you know for polymers, add on this stresslet term by hand, and then you put in the Brownian noise. And then when you let this run, you see that if you take such chains and you hold one end, and what they saw is that for extremely high levels of activity in the system, you could get these amazing sort of a lasso-like formation in these systems. These are systems where extremely high levels of activity in the system. This is something that I first heard at a meeting in Bangalore, and then I thought that maybe this is something we could do experimentally. And that's when we decided to use another method to create these chains. And we used a method which I'm going to describe briefly. This is a method called ice templating, which is a very easy way to prepare these chains. Doesn't even require you to have a function generator and an amplifier and so on. You simply take these colloids in solution in water and you freeze it. You just leave it in the freezer. You've got some polymer that's absorbed on the surface. In this case, it's polyethyleneamine. A little bit of a crosslinker. In this case, it doesn't matter what the crosslinker is. In this case, it's a di-epoxy crosslinker that crosslinks the amine groups on the polyethyleneamine. And if you are at low enough concentrations, you see that you will always get string-like structures. So again, Rajesh, we've never been able to see branch structures ever in these kinds of systems, right? So very simple system. You freeze it, you let it sit in the freezer for long enough that the polymer crosslinks, which is typically of the order of 8 hours to overnight. Thaw it, use, and then you can just harvest these polydispersed chains that you get, and then you can use microscopy to view these clusters that you get, right? Just to give you some sense of the numbers, the average ice crystal size is of the order of 70 microns, and these ice crystals grow at about 0.1 micron per second. I'll tell you why that's important. Now, how do you render them active? So once you make these chains and you harvest them, you've still got the polyethylene on the surface, and what that does is gives you a slightly positive charge, right? So you can then take these materials and then absorb platinum nanoparticles themselves. So you have these tiny particles, and these platinum nanoparticles are less than 10 nanometers in size, and so they go and you have a high enough concentration that you completely cover the surface of these particles. This semi-flexible chain decorated with these platinum nanoparticles on the top. And what that lets you do is very efficiently catalyze the breakdown of hydrogen peroxide to form oxygen and water. And that chemical reaction drives the system out of equilibrium, because you have a continuous chemical reaction happening on the surface, and then you have exchange of the reactants and the products that gives rise to a concentration gradient at the surface of these systems, right? And that then drives interactions in these systems, which is what was modeled by Ronojoy and Sunil through this term here, right? So these are not.
Guru,
yes.
Sorry, the templating thing is done in sort of sheet-like formations of ice. That is, is it a nearly planar thing? Is it a 2D thing, which is why the boundaries are linear, or what? How is it done?
So we've done both, so Sriram, I'll just come back and talk about that in a minute. So these are not done in sheet-like formation. These are isotropic formations. I mean, the reason that these form string-like structures is possibly that they go to the equivalent of plateau borders, right?
Yeah, I was just going to ask that. So that's where they go. So you have polyhedral domains, and then you have just like plateau borders in form. So that's where these guys go. Okay, fine.
So we ran these really trivial Brownian simulations in these systems. You got particles that form, and then you notice that, whoops, oh, where did I go? Yeah. So what you see, and it's remarkable, these are, in a sense, sorry, I don't know why this is moving without my, right? So what you see is distributions of particle aggregate sizes that are very, very similar to what you see in experiments. And you note these at low concentrations you get these lines, but as you go to higher concentrations, you borders and you start forming sheet-like structures. And if you go to higher still concentrations, you can sort of see this in the simulation results. You start seeing these kinds of structures, which really tells me that you have a plateau border kind of system here, and then you've got this interstice between these particles, and then you get these larger structures that form, which are sheet-like in origin, right? So you can take these systems and you can freeze them at very dilute concentrations, volume fractions of 10 to the minus 4% to maybe 10 to the minus 2%. And you see this formation of lots of monomers, but also starting to form these strings. And then as you go to higher concentrations, you start forming 2-particle white tapes, and then if you go to higher concentration still, you start seeing the emergence of sheet-like structures and eventually 3-dimensional kind of aggregates. And what's remarkable is this, right? So we can do simulations. I mean, these are trivial simulations. There's lots of constraints that you impose, and remarkably, so we completely neglect hydrodynamics. It's simply a situation where you take these particles, and as the ice crystals grow, which you don't see in the simulation here, they force these particles into the space between these. So it stays in the liquid phase, and then eventually, as space folds up on itself, it goes into these regions which give you the aggregate structures. But what was remarkable is that if you looked at, in this case, in the simulations, 3 orders of magnitude in the colloidal concentration, and you plotted the distribution of particle aggregates, then across these concentrations, you would see that, so beyond this, your statistics get very poor because you have these large clusters and very few of them, and then you don't get very good statistics. But over about a decade, you see this consistent n to the -2 kind of a power law. Now, this is independent of concentration. If I get sheet-like structure, so I can experiments where you can have directional growth of ice crystals, and if you have these directional growth of ice crystals, the way in which space closes up on itself is very different. So you no longer get this n to the -2 dependence, but this exponent -2 then depends on the size of the ice crystals or the concentrations that you get in these systems. And that's a separate talk, and I think it really has to do with the structure of space as it closes around these dispersions. In this system, in this case, when you have isotropic ice crystals that are growing across a fairly wide range of concentrations, you get this very consistent growth, because what happens is once you define a pocket, everything in that pocket has to collapse into one cluster. On the other hand, when you have these sheets of ice that form, they essentially grow towards each other, and at some point, if you have particles all over, they locally form clusters. So you have a formation of particles that are trapped in between these ice sheets. But as the ice sheets just start to impinge, they then further break up into smaller segments. So really, the way in which that space closes up on itself gives rise to very different power laws for the distribution in these systems. So this is work that we published a few years ago in Faraday discussions, and the other paper is under review in soft matter, and we're getting beaten up a lot on this description. So, but we really believe that's what is happening in these systems. Okay, so again here we can change the stiffness simply by changing the cross-linking time. I showed you the movie for semi-flexible polymers, but you can look at really flexible polymers. This is very hard to get. It's very difficult to get very many of these. You can get these systems that are flexible, and then you can also get systems where you cross-link them for long enough. They're effectively rigid systems, right? And for the case of the experiments that we did relating to the work of Ronajoy and Sunil, we picked the semi-flexible systems. We tracked each of the particles. We tracked in each of the chain, calculated the center of mass of the chain, and then tracked the center of mass of this chain in 2D. It's isotropic, and therefore the X center of mass diffusion and the Y center of mass diffusion are the same. We can see that, and therefore we just assume that the Z center of mass diffusion is also the same in these isotropic systems. So what do you see for passive Brownian necklaces? There's no activity as yet here. You can do these experiments where you have no platinum, but you have peroxide, but you have platinum, but you do it in water, so there is no reaction happening. And what you can plot is the mean square displacement of the center of mass as a function of time, and you see that you get this mean with time, suggesting that you can pull out the diffusivity. And what you see is that as you vary flexibility in these systems, there's really not a very big change in diffusivity as a function of flexibility in these systems. I'll tell you why that's important as we go ahead. These are relatively short systems that comprise of only a few monomers that are linked together, but they're semi-flexible. And given the statistics of the fluctuations, they also obey Zim dynamics. And you see that the diffusivity scales with n to the -0.6, where n is the number of particles in the chain. And that's, again, something we expect to see for these passive Brownian necklaces. So now let's come to the interesting part, which is what happens when you have active systems. Let me see how we're doing on time. Okay, I need to wind up soon. So let me quickly get to this. So when you get to the active systems here, what you see, again, this is just to make sure that you take a single particle, right? So there is no connectivity, a single isolated monomeric particle coated with platinum, and it doesn't seem to matter whether you have peroxide and platinum or any of these systems, you get the same diffusivity. That's as expected, because if you have a system and you have reactions all over the surface and you have a single isotropic particle, you don't expect to see anything interesting happen. However, if you have systems where you have active particles bound into chains, right? And so this is a chain where Brownian fluctuations can take this chain, which and then perturb it perturb it so that you have breaking of symmetry in these systems. Then what you get is a diffusivity that increases the chain flexibility. So if you have a very rigid system, a rod-like system that we saw here, right? This rod-like system is so rigid that it doesn't really get perturbed much by Brownian noise, and therefore this system has the same diffusivity as the passive system. If, however, you increase the flexibility in these systems, and you can sort of, then that breaking of symmetry then allows these diffusophoretic interactions to happen in these systems, so that you get an increase in the center of mass diffusivity as you increase the activity in these systems, right? You never get we ran this at very high activity, but you can never get those kinds of lassoing systems or huge displacements, but you can very clearly see about a 60% increase in the center of mass diffusivity in these systems, right? And that's as a function of the flexibility in those systems. So this was really the first experimental demonstration of the IIT Madras math science model for active chains. You could get these chains that break symmetry through Brownian fluctuations, and the chemical reactions set up these concentration gradients of reactants, and diffusophoresis from this is what drives the activity. And you can see that as you would intuitively expect, right? The flexible semi-flexible chains had higher diffusivity in these systems. What I didn't talk about as much was this n to the minus 2 dependence of the distribution of cluster sizes, and especially the really interesting aspect that Sriram brought out in terms of how this changes when you have different ways in which you ice template these structures. But that's for another talk. So, one of the things that we thought about then is to look at ice templating as a route to three-dimensional materials. What if I increase the concentration in these materials? And so this is my little doff of my hat to technology. And so I'll very briefly speak about this because it's something which is very dear to my heart. This is work that we did again some years ago. Is do this much
hello.
Yes.
Hi, Ajay Sood here from Bangalore. Did you try anchoring one end of the bead and then looking at it?
No, we couldn't figure out a way of effectively anchoring one end. If you have a suggestion on how we could do that, we'd love to be able to. That's the really fast. And Sunil, but we weren't quite able to figure out how to do. So one possibility is to hold it with a laser tweezer, but these are micron-sized colloids, right? And so unless I can anchor a much bigger bead to one end, which should be in principle doable, then we could actually do this experiment where you hold one end and then watch it sort of maybe rattle around in this fashion.
Sorry, I was actually 1 micron is good enough to attach with the optical tweezer, or you can have biotin, some linkage on the substrate, and then put the streptavidine on that, and then because that is the way this people do when they want to unzip the DNA.
Okay.
That's very standard practice in this, because then I'm saying you can really see what you're looking for.
Right. So my sense is we will not see that, because when they did not tether one end and they looked at these very high levels of activity in the simulations, what they saw was very large tumbling motions of their chains. We never see that. So my sense is that level of activity is outside of what can be done experimentally, at least using these kinds of systems. And we aggressively drove this to very high peroxide concentrations. And so my sense is we might not see that, but it would certainly be very interesting to look for what they have. I mean, what would it show when you tether one end? But that's something we never really got around to doing in these systems. But thank you very much. That's a very interesting suggestion.
Yeah. Do you have a upper limit on the size of these chains you get by this ice templating?
So
is it because your things are always like 10, 15 particles, is it?
Right. So we struggle to get chains which are larger than 15 particles in size using the ice templating method. We used it because it was very of chains using the other method that I described, where you line them up in a field, and there you can easily get much longer chains. So that's not a constraint. But the ice templating method does not really give you. It's an easier method to implement, but it gives you polydispersed chains. But if you go to higher concentrations, you see a transition from chains to tapes and sheets and so on.
Okay.
And so that's not a good way of going to much higher chain lengths, in my opinion.
Yeah. Thank you.
So.
Thank you.
Thank you. So in the last part, let me very briefly talk about what we can do when you go to much higher concentrations of these particles. And this is work that I did some years ago. So the philosophy that we use is the same. You take particles and coat them with a polymer, and you cross linker, and you freeze this dispersion, and you can get these large macroscopic things. You can hold them by hand, and these are almost entirely particles, right? So if I look at burning off the organic is barely 10% in these systems. So you cross-link this in the frozen state, and that's important because what that ends up giving you is systems which are, even though they're almost all particles, you can get systems which are remarkably elastic, right? You can take these systems, they're in this case it's filled with water, but you can also do them dry, and you can compress them to 1/10 of their original size. And what's really remarkable in this system is that when you let go of these systems, you can get them to essentially elastically recover to the original shape in this system. So these are highly filled, over 90% by weight is particles, but you can get systems which are extremely flexible. And so just one last slide, since I'm out of time. What good is this? We've made things, for example, so this is a fire retardant polyurethane. And so if you're looking at seating in public transportation and buses and airplanes, you need to have highly fire retardant systems. But even these systems, when you stick it in a flame, will burn, right? And the way you make them fire retardant, number of brominated compounds, really nasty compounds in here. Our systems are sponges which are essentially fireproof, right? You can see that they are flexible like the foams are, but when you stick them in a flame, there's very little to burn. When you pull it out, in fact, the flame will actually self-extinguish in these systems. And so, this is actually, in a sense, a platform technology. It's not just good for making seats to sit on, but we've made flexible electrodes. We've made sponges for solvent cleanup, biocompatible implants. You can make them entirely biocompatible by looking at hydroxyapatite and gelatin, and we've implanted these in mice to show that you can get variable stiffness sponges that can be implanted to guide cell growth in mice and so on. So I just wanted to stop there to comment on the fact that there are implications of this beautiful science for technology as well. But I want to leave you with this thought that colloidal self-assembly is really a route to get very nice tunable model systems, right? And to me, I think the joy of doing this is it's very inexpensive, simple science, simple in the sense that it doesn't take a lot of resources to implement, but beautiful, interesting physics can result from these tabletop experiments. What I'm especially fascinated by is this effect of connectivity. I think this idea of connectivity is something which we need to probe deeper. There's a lot of very interesting things that come out of covalently connecting these structures, and I think there's a fertile scope for doing things in this space. I think the results that I've probably not presented in other meetings before, which are relatively new, are the fact that you can form these helical structures at intermediate stiffness chains. This we've talked about before, is that active chains diffuse faster as you go to more flexible sponges. And finally, just wanted to comment on the fact that there are implications of these kinds of materials for technology, and therefore a lot of opportunities in this area. So thank you very much. And again, thank you for inviting me to speak in honor of Aditi's memory. We did overlap for about a year at IIT Bombay, and I'm delighted to be able to speak in this symposium. Thank you very much.
Thanks a lot, Guru. It's a nice talk. I think now it's open for questions. Please, if you have a question, please ask. Then we'll go to the chat room.
Hi, sorry, Sriram here. I have a question.
Please go ahead, sir.
Actually, I have sort of two questions. One is that you said you can get sheet-like structures. One, there might be an opportunity there to come up with a realization of Taylor's swimming sheet if you can activate the structures. I mean, this classic model of self-propulsion of a waving sheet. So have you tried making active sheet-like structures and looking at what they do? Ribbons, sheets.
I have a graduate student I'm trying to persuade to look at sheets. In fact, so I'm hoping that he will decide to do. There's lots of interesting things we can do. We can actually make sheets, and we can selectively burn out certain. So if you make a sheet, say I'm guessing it might be too stiff, but we've actually have a very cool way of burning out certain holes, right? So you can just take specific particles in that sheet, burn them out to make them. Well, my collaborator calls it a holy sheet, right? So holy shit, right? So you can get these sheets, and those will hopefully be a lot more flexible. And I'm hoping to be able to work on that with this student.
So the other question I had is, since you also make helices, can you plant these helices in such a way that they can turn, but stay attached to something? And then can you therefore make a bacterial flagellum, a rotating flagellum? Again, if you make it active.
Yes. I don't know. So Bipul has graduated.
Easy,
this is something which.
But I just, given that you have all these things, I just thought
I think this is fascinating. Like I said, I think we've only scratched the surface. There's so much we can do. We didn't expect to see helices. Our naive expectation was to start seeing things like chain folding and get them to collapse, right? We were stunned when we saw helices, and it's one of those sort of moments where you think and kind of obvious that there should be a chance of forming helices. But when we started the experiments, we hadn't anticipated that, and so for us, it was beautiful surprise.
Cool.
Yes. Hi, Guru.
Can I ask a question?
Please go ahead. Please go ahead.
Hi. So, Guru, coming back to this sheets formation and others, do you think if you had some kind of a surfaces on which these can absorb, you can have other kind of structures also that can emerge? There are these phase diagrams of different small polymers. When they absorb on surfaces, you have all the way from layered structures to collapsed structures. So is it experimentally possible to sort of induce the structures that you want by introducing some kind of a surfaces so that they can absorb and then remove them and study? I was just very curious about this.
Actually, those are actually, thank you very much. It's a very nice suggestion. And I think experimentally, it's very doable, right? And it's a very, very nice suggestion, especially if you can, take certain particles out and make them more flexible. To look at the effect of that on absorption is actually a wonderful problem, right? Yeah. But that's not something we had thought about. But this is certainly something we can. And I think thank you for your suggestion. We probably will do it. And so, Vani, I'd like to be in touch when we do these experiments. I will let you know what we find.
Yes. So there was some work we did on this absorption of polymers on curved surfaces. And they take extraordinary shapes depending on you vary the interaction between the polymer, the solvent, and the adsorption interaction. You can get all sorts of structures. So I was just wondering if you can get those structures and then take them out of from the surface. Probably there's a wide variety of phase space that you can have control on. That was the reason.
We can also look at them while they're adsorbed, right? Because if I look at it on
exactly,
we can study. Yeah, absolutely. Yeah.
Okay, great. Thanks.
Yes. Basa, you have a comment. Please go ahead.
Yes, please.
Yeah, Guru, I have a comment about the 2D sheets that was asked. So I think the interfacial assembly would be a really nice way to make these 2D sheets. Essentially confine them at the interface and then cross-link them would be a nice way, I think.
Yeah, absolutely. And it's much easier to get a higher yield of sheets with an interfacial assembly. And so we weren't looking to use interfacial assembly techniques to make sheets. And that's something, again, we can come back and talk to you I think you have a lot more expertise. By the way, the student I'm trying to convince to work on this is a former student of yours, Santosh, and so hopefully he'll work on some of these.
Hi Guru, there is a question from Rajesh Ganapati, who is watching in live stream. What happens to the diffusivity in the orientational degree of freedom when the flexibility is increased? It's in the active chain context.
Right. So what happens to the orientational
degrees when you increase the flexibility of the chain?
I don't remember. Sorry?
I'm also watching it on WebEx. This is Rajesh here.
Rajesh. Hi, Rajesh.
Fascinating. Rajesh, that's a good question. I don't know the answer to that. Right?
So the reason I asked was because you had more or less rigid filaments, right? And I was wondering if there's a non-trivial coupling between orientation and translation that leads to enhancement.
That's a good question. I don't have an answer to that. Yeah, maybe this is something Bipul can do with Manasa, because he's working with her now. Maybe this is a nice problem for them to also look at, because I don't think we ever looked at that. I mean, we have the data, but I don't think we looked at what that is. We were focused on distribution that we didn't look at that aspect. But that's a really good point.
Thanks.
So any other question from the audience? So Guru, I just would like to have one comment from you. When you increase the flexibility, do you see this chain folding? You don't see the helices. You say is chain folding occurs at higher flexibility?
We don't see chain folding. We see collapse, right? There is no. So our thought was to essentially mimic things like polymer crystallization, right? So for polymer crystallization, because of the connectivity, you have folding that gives rise because you simply can't stretch it out long enough for flexible polymer chains. And so that's a context in which we wanted to see this. So what we would do is essentially put down a patterned surface, an epitaxial surface, watch these things absorb, and we were hoping to see it fold. And we could never see it fold. And at that point is when Bipul discovered that rather than folding, our epitaxy was these things getting strung up and folded. But what we saw was these things forming helices. And at that was sort of a aha moment saying, of course, it could also form a helix, and we hadn't considered that. But, either on surface or in the bulk solution, we really never saw folding, right? And I don't know why. I mean, again, like I say, I hesitate to make a connection between real molecular polymers and these because there are differences, there are very significant differences. And maybe these systems do not show, at least, so what you need to have is sort of local rigidity and yet driving forces that require you to collapse, right? That gives you this folding. Maybe those systems are not easily realizable for the model that we have. So I saw a question from Pinaki on chat, but it disappeared.
Yes.
So I
can read it for you. There is a question from Pinaki. He says, can one control the elastic property of colloidal sponges? Control the elastic property of sponges.
So the modulus we can tune orders of magnitude, if that's what he means by. Is that the question? Can I change modulus? I can change the modulus of magnitude by changing.
Pinaki, are you watching? Can you please go ahead?
Yeah,
Pinaki?
can you hear me?
Yeah, Pinaki, we can hear you. Please go ahead.
Yeah. So how do you? So one of the mysteries is what is the elastic property of the colloidal sponges, and how can one control it? I mean, for example, if I'm doing atomistic simulations, it's very difficult to get this this elastic property for these kind of structures. So how does one experimentally tune that? It would be very interesting to know.
Great question, Pinaki. We actually spent many years. So Karthika's thesis was entirely on this, and this is something that we understand really well. What happens in these sponges is that it's crucial for you to get elasticity. It's crucial to crosslink in the frozen state. And so what happens in the frozen state is that the conformation of the polymer chain that's absorbed on the colloidal particle is expanded, and therefore you can have effective cross-linking between these sparse polymers. There are other ways by which you can make these sponges. You can essentially, the traditional way a freeze-dried structure is you freeze it and then you expose it to a very high vacuum. You sublime the water. You get the structure, and you can then subsequently cross-link, but you can never get. That's because under those conditions, air is a bad solvent, and then that collapses the polymer chain. If you essentially get a melt of polymer chains between the particles, then it doesn't matter. The melt, you're always at theta conditions, and you can always get elastic sponges, right? So the key here is that the polymer is adsorbed on this, and so there is a possibility of desorption, and the polymer essentially forms this. And what you deform, and you don't actually deform if the particle is too rigidly coupled to the polymer, then you have a problem.
Okay.
And so, again, this is sort of something that we discovered by accident, but I think we understand how this works really well now. And I have a series of papers on this, which I can send to you if it's of
Sure.
interest.
Yeah. Okay. Great. Thanks.
Do you have any more questions from the audience? Hello, if somebody is trying to ask, I can hear noise. Okay, I think I don't see any questions in the chat window either, not also in the YouTube. In that case, I think thank you Guru a lot. It's a very nice talk, and taking time out on a Saturday to speak to us. Thanks a lot.
It's a pleasure, and thank you for inviting me. Thank you very much.
Now I would like to request my colleague, Dr. C.V. Krishnamurthy, to chair the next session. Over to you, C.V.
Hello, can you hear me?
Yes, we can. We can hear.
Yeah. We are now coming to the last speaker, Professor Madan Rao. I'll introduce him to you. Not that he needs an introduction, but then let me introduce Professor Madan Rao. Madan Rao is a theoretical physicist at the Simon Center for the Study of Living Machines at the National Center for Biological Sciences, TIFR, in Bangalore. He received his PhD from Indian Institute of Science, Bangalore, in 1989, and postdoctoral training at Simon Fraser University, Vancouver, in Canada. Subsequently, he held positions at the Institute of Mathematical Sciences, Chennai, and Raman Research Institute, Bangalore. His work spans the broad area of non-equilibrium statistical physics and soft matter. He has contributed to the field of active matter from its inception, in particular, its applications to cellular and tissue biophysics. His current research interests include how non-equilibrium processes facilitate information processing, computation, and control within cells and tissues. Over to Madan.
Yeah, thanks, Krishnamurthy, and thanks Manoj and Sumitra, and rest of the organizers of this conference held in memory of our dear friend and colleague Aditi. I've had the privilege of collaborating both with Aditi and with her sister Maitri, and it's really a great honor for me to give this talk. I hope you can hear me. And
yeah, we can hear you.
Okay. Oops. How do I change the slides? Yeah, okay. So here's a picture of Aditi at a very different stage of her career from what, you saw the two pictures that Guru and Christina showed. This is a picture of Aditi as a PhD student at the physics department of IISc. And I thank Sandeep Krishna for this picture. As Manoj said, Aditi has left a lasting legacy in the form of her many papers written during her PhD, together with Shivam. And these papers, I mean, as I mentioned before, it's quite rare for a PhD work to launch an entire field of active soft matter, and this is what happened at these several papers, culminating in this review article that Christina showed. We again had the privilege of being part. So, since living systems constitute the most profound realization of active systems, a field which Aditi contributed so immensely. Let's focus on the cell. Okay, cell being the fundamental unit of life. This talk is going to be slightly biological, so unfortunately, I'll have to also give you some information and phenomenology, but I'll try to restrict that to a minimum. So it's been recognized that the cell is a driven, organized state of matter, which involves the consumption of energy and the inheritance of information to give rise to form. And this is what I've mentioned in these two lines here, that the cell, which is the fundamental unit of life, is a self-sustaining organization of matter maintained out of equilibrium locally and persistently by the consumption of energy, which the cell itself produces. Cellular organization is derived from inherited information and self-organization and requires constant energy conversion flux. And to get an estimate of the amount of energy consumed by a cell, one can sort of estimate it to be around 10 to the 7 ATP molecules consumed in a cell per second. And the way to get at this number, a back of the envelope calculation, which was described in Rob Phillips' Biology by Numbers, is to say that a typical human of a given size consumes 2,000 kilocalories per day, which translates to around 100 watts. And knowing the size of the cell and the size of the human being, you can work out how many cells does a typical human being have, and that's a number around 10 to the 13 cells. And assuming that all cells consume the same amount of energy, you get a number which is 10 to the 7 ATP molecules per cell per second. Okay, and that's a fairly large amount of energy that is primarily used to organize matter and components of the cell. Yeah. Okay. So indeed, the way matter is organized in the cell is in the form of compartments, and cellular compartments house very specific chemicals, and they have a very specific organization in the cell. And this is a cartoon of the cell shown here in colors. In these fake colors, you see various membrane-bound compartments. These compartments are typically membrane-bound, as I said, and they have a definite area, which is listed here for different cellular organelles, and they enclose a very definite volume. So the question, of course, that one would like to ask in biology is, how are these compartments assembled in the cell? What are the driving forces that assemble them? What determines the size and shape of these organelles? What determines the number of, for instance, these organelles that I'm going to talk about, and so on? What determines the spatial position? All these are repeated quite remarkably consistently in cells as they undergo cell division. You see the same number and same relative positioning of the organelles. And how is this achieved? What I'm going to be focusing on here is, if I can see the cursor, what I'm going to be focusing on is these red organelles here. It's called the Golgi apparatus, and I'll tell you about the remarkable assembly of this Golgi apparatus in a typical cell. So please stop me if there are any questions, because since there is a bit of information that one needs to provide, I'd like you to keep pace with it so that you can understand the rest of the talk. So if there's any questions regarding any of these, please do ask me. Yeah. So of course, non-equilibrium. So the point is that the whole story that I'm going to talk about is that this organization of these particular organelles, like the Golgi, the nucleus, these green objects called the endoplasmic reticulum, all these objects are being assembled in a non-equilibrium manner, and which will require the consumption of energy. And this is typically what happens in a cell. And so the question now is, how do we understand the physics of non-equilibrium assembly? Non-equilibrium assembly, of course, is not is known in non-living systems. And for instance, what you see here is the many ways in which water can turn into ice. If you cool water very slowly, then it forms an equilibrium ice crystal, shown here. But if you cool it very fast, then it forms these myriad of ice flake structures that one sees. And this comes about because of the interplay between the rate at which heat is diffuses out of the system, and the free energy gain in going from water to ice. And it's this interplay between these two time scales that gives rise to these very strange and beautiful ice-like crystals. So this is a non-equilibrium self-assembly, and this is the kind of self-assembly that we're talking about. However, the difference, whereas here the non-equilibrium assembly was being dictated by the rate at which heat escapes from the system, and it's coupling to the density of water molecules. In the system that I'm going to talk about, is driven locally by active chemical reactions. Okay, so so at the heart here of all the self-assembly are these machines. Okay, these machines which consume energy. These machines are called GTPA cycles, and they should be thought of as being discrete chemical states which can be discrete chemical sort of reactions which consume energy. Okay, and these discrete chemical reactions are at the heart of a lot of non-equilibrium processes that happen in the cell. Okay. So, for instance, these GTPA cycles, which involves, which I said, involves the consumption of energy, drives the fission and fusion of little tiny vesicles, which go on to assemble these large structures. So, what I will be interested in, and what a lot of people are interested in, is in how these organelles. This Golgi is drawn here, for instance. The endosomes are a system of organelles which reside all over the cell cytoplasm, and the mitochondria, which is the energy powerhouse of the cell, is also a set of reticulated organelles which are driven by the active consumption of energy and by fission and fusion processes. Okay, so what we have been interested in for a while is how do we understand these cellular morphologies, the size of these cellular organelle morphologies, or the size of these organelles in terms of the non-equilibrium dynamics of fission and fusion of tiny vesicles, which in turn are driven by these non-equilibrium chemical cycles. Okay. So the questions we'll be going to ask is, what is the non-equilibrium control of size, shape, relative position in the cell, and the number of these systems? Okay. And with special focus on this Golgi system. Okay. So now I'd like to discuss the common elements in these three kinds of architectures: the endosomal system, the Golgi cisternal system, and the mitochondrial system. Each of these system of organelles are actually membrane-bound organelles. Okay, and they are membrane-bound organelles which have multiple lipids and membrane proteins, and the shape and the dynamics of the membrane is governed by membrane elastic forces. Okay, so this is one common theme between all these three systems. So clearly, one of the driving forces is membrane elasticity. The other important ingredient that needs to be considered is the fact that there is a dense cytoskeletal meshwork in the cytoplasm, which gives rise to the overall cell rigidity. And these organelles, both all the mitochondria, the Golgi, and the endosomal system interact constantly with this cytoskeletal meshwork. The third, of course, is, as I alluded before, is that each of these organelles are formed by the stochastic and non-equilibrium fission and fusion of tiny vesicles onto it. Okay, so these are the three driving features, the driving forces that go to build this kind of non-equilibrium self-assembly. I'll repeat, you need to consider the membrane elastic forces because all these organisms are membrane bound. You need to consider the fact that they are interacting very closely with the dense cytoskeletal meshwork, the actin and myosin that Christina talked about in her first talk. And they're also formed by the non-equilibrium fission and fusion of tiny vesicles. And it's these three ingredients that we believe are control the size, shape, and relative positions of the system of organs. Okay. So let's spend some time on the first of these, namely membrane elastic forces. And I thought I would put up a few slides because there are students in the audience. And while these are common knowledge to those working in soft matter physics, this might be a good set of ideas or ideas that the students might like to think about. So let me spend some time on describing what membrane elastic forces are. Okay. A membrane, which is typically a bilayer like this, okay, a lipid bilayer, is described by what's called a curvature elasticity. Namely, at length scales much larger than the thickness of this bilayer, you can think of the membrane as being a two-dimensional sheet. And the two-dimensional sheet is locally described by its local curvature. The local curvature has, because it's a two-dimensional sheet, you can define two kinds of curvature. One is the mean curvature, which is the sum of the two principal curvatures shown here, R1 and R2, and the Gaussian curvature, which is the product of the curvatures 1 by R1. Okay. So these two curvatures form what's called the principal curvatures of the two-dimensional surface. And if I describe these curvatures locally at every space point, then I totally define the surface of the membrane. The energy of the membrane is given by the famous Helfrich Hamiltonian. Okay? And the Helfrich Hamiltonian says that the elastic forces that are relevant for to describe shape distortions of the membrane are these three. The first term is that there's a surface tension. Namely, this is the Lagrange multiplier which keeps the area of the membrane fixed. Okay? The surface tension acts as a Lagrange multiplier which keeps the area of the membrane fixed. Namely, lipids don't come out and you don't lose or gain lipids. Okay? And the second is this curvature energy, and is written in this form because the idea is that any deviation of the curvature, local curvature, from a rest value called the spontaneous curvature costs energy, and this is like a Hookean term which describes the curvature elasticity of the membrane. Okay. The third term is this Gaussian curvature. Sorry, is the Gaussian curvature K, and is these three, namely surface tension, mean curvature square, and the Gaussian curvature that goes to describe the elastic free energy of a membrane. Because the membrane organelles that described are closed, there's a Lagrange multiplier which goes to fix the volume of the enclosed membrane. Okay, and that's given by the pressure here. So this Helfrich Hamiltonian has three parameters. There is sigma, the surface tension, kappa, the bending rigidity, H0, the spontaneous curvature, and kappa G, the Gaussian curvature. Gaussian curvature modulus. And these three, kappa, H0, and Kg, the bending moduli, kappa and kappa G, and H0, the spontaneous curvature, are material properties of the membrane and depend, of course, on the nature of lipids and proteins that exist on the membrane. This, of course, is the sort of minimal Helfrich Hamiltonian or minimal elastic description of the membrane. One could include, if one thinks it's important, quantities such as variable membrane thickness. After all, here we have assumed that the thickness of the membrane is fixed. But in real biological membranes, the thickness of the membrane can actually be spatially and temporally varying. And so there will be an energy cost to the variable membrane thickness. There's an asymmetry in the membrane bilayer. The upper leaflet of this membrane is different from the bottom leaflet in terms of composition. And therefore, this would give rise to an additional features in the Hilfrich Hamiltonian. There could be embedded proteins which are anisotropic in shape. They would couple to the curvature elasticity in very specific forms. And these membranes, as I said, are closed membranes. They enclose a solvent. The solvent has a particular pH, and this could affect the energetics of the membrane. So that you could add in a very systematic way these additional contributions. But for the time being, let's just focus on the simplest of elastic energy descriptions for the membrane. Okay. As I said, kappa G and H0, the elastic moduli and the spontaneous curvature are parameters in the free energy, and these parameters depend on the nature of the proteins and the lipids that are embedded in it. Minimizing, so at equilibrium, one is instructed to minimize this energy subject to the constraints that you have. And this gives rise to a variety of shapes, shown here the simplest kinds of shapes that you get: spheres, cylinders, saddles, but you can get all kinds of combinations of these shapes. And for a long while, physicists have been describing the weird shapes that one sees in biological in cells via this equilibrium Hamiltonian. But over the last 10 years, there's been a realization that such equilibrium descriptions of biological membranes don't suffice, and one needs to include active forces coming from a variety of processes, here the active fission and fusion of tiny vesicles. Okay. The next ingredient common feature that I talked about was the interaction with the cytoskeleton, the microtubules and the actin filaments that pervade the cell. And what you see here is a picture in yellow is the Golgi. It's a very low resolution picture, so you don't see the individuals' compartments. But you can see that this is entrapped in this red microtubule background. Okay, so there are two things that happen here: that the microtubules, the cytoskeletal meshwork, facilitates the trafficking of tiny vesicles. You can see that in many of these pictures, up there. But they also provide a scaffolding, okay, an entrapment of the Golgi system, okay? And this will become important in my subsequent talk. Okay, so the interaction with the cytoskeleton is a crucial element, and we're going to put that in as a feature of the organization of the cellular compartment, of these compartments. Finally, I want to describe the fundamental importance of non-equilibrium fission and fusion as a dominant mechanism for describing the shapes of these biological membranes, a feature that has been had been ignored on earlier occasions when one tries to describe the shapes of these membranes. And I want to sort of convince you that considerations of both timescales and forces drive you to state that one needs to, in fact, include these non-equilibrium fission and fusion processes. If you look at, if you analyze the experiments, experiments which done by Rothman et al., Weiland et al. In the Rothman's group in 1987, these are experiments which involve FRAP, fluorescence recovery after photobleaching. An analysis of those experiments suggests that the timescales of fission and fusion events is around 10 to 100 milliseconds. Okay, this is an old experiment, and therefore this might be an overestimate of the timescale, but I would say it's around, let's say it's of the order of 1 millisecond. Okay. So 1 millisecond is a timescale over which little tiny vesicles bombard the set of Golgi compartments here. Okay. These vesicles come from the endoplasmic reticulum, and they move towards the Golgi and fuse onto the Golgi, and vesicles then fission out. Okay, as I showed in this movie. Okay, there's a constant bombardment of vesicles in and out of this Golgi. Okay, and that time scale is around a millisecond. Okay, now let's compare.
When you say that time scale is around a millisecond, you mean you get one such bombardment per millisecond, or something happens in a millisecond during that contact?
So this is the time between events. Yeah, as I said,
across the entire cell.
Across the entire goal.
Across the entire goal,
yeah, that's it. Yeah, so it is pretty fast. Things are coming at a very rapid pace. And of course, what you want to do is to compare this to equilibrium relaxation timescales. For instance, you would like to compare this to the membrane lateral diffusion timescales, which can be simply obtained by looking at the area of a typical Golgi. The size of a Golgi is around the size of a Golgi is around a micron in size, and so is a micron in size, and so you get a typical number for the area, which is given here, around 100 micron square in area. And if you divide it by the diffusion of lipids, it's around 1 micron square per second. You get that you find that the lateral diffusion times is around 50 to 100 seconds. Okay, which is much longer than the time scale over which the vesicles keep bombarding the membrane. Okay. Moreover, if you look at shape relaxation times, namely, which is defined as if I create a bump in the membrane of a certain size L, okay, so the membrane size is R, the bump that I've created is a size L, and the viscosity of the solvent is eta, then I can calculate that how long will this bump that I've created relax to its equilibrium flat configuration. Okay? And that time scale goes as by this formula, and is around 1 to 100 seconds. The higher is the viscosity, the longer is this time scale. The higher is the bending modulus, the restoring force is high, and therefore that time scale will decrease. So putting in numbers.
What's the little l in the denominator?
Say again.
What's that little l in the denominator?
The little l is the length scale of the bump. Okay. So L by R is like the wave.
Then you need a wave number cubed as well in the denominator. Because
so that is the wave. So L by R is the wave number. Yeah, L by R is the wave number cube.
No. Anyway, okay. I'll fight with you about it later.
Yeah.
Madan.
Yeah.
There's a question from Vandana Yadav. Can you emphasize on the pressure term included in the membrane Hamiltonian?
Can I comment on that?
Yeah.
So this is an osmotic pressure because the volume of the membrane. There's a certain volume that is enclosed by the closed membrane, right? And so there's an osmotic pressure difference between the inside and the outside.
Okay.
And so that's the origin.
My question is it mediated by the proteins also inside the cells? Like this is affected by the motor molecules are also giving a pressure on this membrane that is also included in this osmotic pressure?
So there could be proteins inside the membrane and inside the enclosed volume. And this would certainly contribute to the pressure.
Okay, that pressure. Okay, Thank you, sir. Thank you.
Because as I said, it's the osmotic pressure, so it'll depend on all the particles that are enclosed inside. Okay, so the point here is that the time scale between these non-equilibrium fission and fusion events, which are non-equilibrium processes, is much smaller than the time scales over which the density and the shape relaxes. And so clearly the non-equilibrium processes are an important driver to consider. Okay? Just to give you an estimate of the scales, as I said, the size of the membrane is around 1 to 10 microns. The typical size of a vesicle is around 50 nanometers. So you can see that the size of the membrane, the Golgi, is much larger than the size of the typical vesicles that bombard it and come out of it. Okay. Okay. Now this is where the activity, the active chemical reactions come in. Every fission and fusion event, which makes a vesicle fuse onto the Golgi or removes a vesicle from the Golgi, involves a mechanochemical cycle. Okay? The discrete chemical reactions, which are driven by energy consumption, which feed into this fission and fusion process. Okay? So here I've drawn the fusion cycle. This is a vesicle which is wanting to fuse onto this Golgi membrane here, and it first has to dock onto the membrane via proteins. This involves the consumption of energy, and then there is a zippering of these proteins, which then opens up a pore, and then eventually fuses. We will not be interested we'll be only interested in timescales which are larger than the fusion cycle and the fission cycle, and length scales which are larger than the size of this tiny vesicle. And so I'm going to ignore all the microscopic details, microscopic physics that goes into each of these processes. Okay. But what we'll be interested in is the fact that there are transition rates to go from one discrete chemical step to another. And these transition rates violate detailed balance, and so there's a finite current that is generated along this loop, okay, along each of these fission loops and fusion loops. This finite current eventually goes to transport area. Every fusion event will fuse this area of this tiny vesicle onto the Golgi membrane. Therefore, you're going to add onto the membrane area. And is also going to transfer some amount of the volume of the cargo vesicle onto the volume of the membrane. For some reason, the slight movement is very strange. Okay. So with every fusion and every fission event, there is a transfer of membrane area and transfer of volume. I don't know why this is happening, but okay. There's a transfer of membrane area and transfer of membrane of volume. And as I said, the time scale between these fusion and fission events is around a microsecond. One can estimate a typical value of the force, okay, that is required in order for this fusion to happen. And one way to estimate that is to say that when I bring the tiny vesicle to the vicinity of the Golgi membrane, then I need to extrude the volume of the volume of water in between. Okay, so there's a shearing force that is going to be generated by bringing in this tiny vesicle onto and making it fuse onto this membrane. But can calculate the force that is required, the typical force that is required in such a process, if I want to bring this tiny vesicle onto the membrane over a time scale of a millisecond. And that force is around 10 piconewtons. So you can see that is a pretty large force that you need to expend in order for typical fusion and fission events to happen. Okay, this is comparable to the membrane elastic forces. So both in terms of time scales and in terms of forces, this is a relevant, fission and fusion are relevant considerations to try to understand the shape dynamics of the membrane. So here is a flow chart of the dynamics. every time a vesicle fuses, let me see here, like so, every time a vesicle fuses, okay, it transfers area, it transfers volume, and it transfers momentum. That is, there's a net force acting locally on the membrane. Okay? This force can be quantified by a force dipole, which can be computed by which can be computed in this chemical cycle that I talked about. These active fluxes and forces, in combination with membrane elastic forces, drive shape changes of the membrane. The membrane velocity then couples to the solvent velocity, which then acts back on the membrane, and the membrane velocity then the membrane velocity acts back on the membrane. Giving rise to there's a flow chart that you want to write down, which is the membrane dynamics, which includes forces coming from activity and elasticity, go to change the membrane shape, which dissipate momentum into the membrane, which then acts back on the membrane. Okay, so I'll just pictorially say what other kinds of equipment. Yeah.
Manoj here. So could you elaborate a little more on the physical origin of that force type picture that you showed?
Right.
Where exactly does the forces come from?
Right. So there are many places in this fusion cycle, let's say, which contributes to the forces. When it first docks, what you need to do is you need to bring the vesicle towards the mother membrane over a time scale which is around 10 milliseconds. Okay, let's say 1 millisecond. Okay, that will mean that you need to drive the intervening fluid away from that from this layer, so that to facilitate the fusion of this vesicle onto the membrane. Okay. To do that, you'll have to that will involve shear stresses of the fluid. Okay, and so I can calculate what is the power dissipation in that. The power dissipation is just given by the viscosity multiplied by the grad V, who is the strain rate square, integrated towards this region. Okay.
Okay. Thank you.
Is that okay? And it's that, and since you know the solvent viscosity, you know the length scale, and you know the typical velocity, you can calculate what is the power in bringing this vesicle towards this membrane. And
so
that
you can
number
estimate the magnitude of these forces using these arguments.
That forces is around 10 picograms, right? So that is the first level of the of force. That simply in bringing the vesicle to the Golgi over a time scale of a millisecond, you need to expend some energy. Okay. The second part of the energy comes in infusing this. This requires you to make a hole here, and therefore you need to climb an energy barrier.
Okay.
And that energy is comparable.
Okay.
Yeah. So yeah. Okay. So just to give you some feel about the wave aspects of the dynamics of this, let me just state the following: that every time, as I said, you bring in a vesicle to make it fuse to the Golgi membrane, you're going to deliver mass. The local mass, the change in the local mass of the membrane of the Golgi, is equal to the sum of these three quantities. It'll be equal to the mass flux coming from fission or fusion. Once I make the vesicle fuse onto this, there's going to be a surface diffusion. So locally, the mass is going to change. So that's the second contribution. There'll be a surface diffusion term. And the third is because there's a spontaneous curvature, a local membrane curvature will kinematically go to change the local mass. So these are the three terms that you get in your local mass equation. Together with a flux of mass, there's a flux of volume. Every time I fuse a vesicle onto the membrane, I bring in a little volume. The change in the local volume is given again by the volume flux per fission and fusion event, and plus a possible volume flux coming from permeation. So the second term is a passive contribution to the volume flux. In addition to these fluxes, there are forces that are applied during every fission and fusion event. And what you're instructed to do is to locally balance the tangential and normal stresses. Okay? So the local balance of tangential and normal stresses is the following: that the fluid stresses, given by the Stokesian fluid outside, is locally equal to the membrane elastic stress plus the active stresses that I talked about. This has been resolved both tangentially and normal to the membrane. Finally, there are boundary conditions that needs to be satisfied because the membrane is embedded in a fluid. The boundary condition is that we take is a no-slip boundary condition, which says that the membrane velocity is the velocity of the membrane is equal to the fluid velocity at the membrane plus a volume flux coming from the fission or fusion. Okay? This is a slightly non-trivial consideration, and we could discuss this later if you. Moreover, in addition to this no-slip boundary condition, the membrane is 2D. The incompressibility of the 2D membrane is that the divergence of the membrane velocity is equal to the mass flux due to fission. So these are the 4 equations written in words here, which go to describe the shape dynamics of the membrane subject to active fluxes of material coming in and out. Okay. Any questions on this? Okay, so if there are no questions, then I'll yeah, skip that. Okay. So having written these kinds of equations, we can ask what are the Nilima has a question. Yeah. Nilima? Hello? I think Nilima had a question. So
Yeah, I see that, but
okay, maybe she'll come on later.
Yeah, I think you just
okay.
you carry on.
Okay. So before once one writes down such equations, of course one needs to try to solve them, and these are quite complicated. Yes. So Nilima asks that I missed that. Maybe you can see
it. Your scales are overlapping. How do you disentangle that?
With scale, sorry.
Okay.
Yeah. Okay. So we will consistently look at scales where we are looking at. So we are going to. Okay. The way I've drawn it here is, of course, draw a tiny vesicle which is fusing onto the membrane. But in the mathematics, this is going to be assumed to be a point. Okay. That is, we're going to be looking at scales which are much larger than the size of the vesicle. But despite that, every fission and fusion event will add a certain area and volume to the Golgi membrane.
Madan, and Nilima is referring to the time scales. The question was on time scales.
Oh, okay. So yeah. So when I say that I'm going to look at the equations that I wrote down are so for the force balance equation and the volume flux and area flux equations are defined over time scales which are longer than the cycle time. Okay, so I'm going to integrate over the cycle time, and at the end of this cycle time, I would have delivered some amount of area. So it's disentangled from the microscopic transition time.
There is another question, Madan.
Yeah.
This is from Shakuntala Chatterjee. Do you have any conserved quantity in your model?
Do I have any conserved quantity? Yeah, so things are, because of this fluxes that come in and out, you're explicitly breaking the usual conservation of density and so on. There is of course volume. There's of course momentum conservation, and since these are high viscosity Stokesian fluids, that gets translated to this force balance condition. Okay, but apart from that, apart from this local momentum conservation, there are no other conserved quantities. Okay, is that okay? The lack of conservation is described by the mass flux and the volume.
Yeah. Okay. Fine. Yeah, she says okay.
Okay. One of the I'll just before one tries to solve these equations, one can make some general statements arising from the form of these of the equations for the area, volume, and forces. And there are three statements that one can make. One is that activity renormalizes the tension, and in fact, the tension is such that it increases. That every fission event increases the tension, every fusion event decreases the tension, and this should be intuitively clear because every fusion event will add mass locally, and so it will make the membrane more floppy. And this is consistent with the mathematics that follows. In fact, fusion events, when it makes fusion events which go to decrease the tension, if there's a lot of fusion events, you could drive the tension to be negative, and you can in fact then see that the membrane gets unstable under spontaneous tubulation, and this has been seen in artificial membrane experiments by Patricia Bassero's group. The next two, the other feature that I'd like to highlight is that this the equations automatically suggest that there's a spontaneous segregation of fission and fusion events. Yeah, and this is interesting to biologists because it would imply this prediction would imply that the fission events and the fusion events have to be segregated on the Golgi, and indeed there is evidence that this is so. We need to understand this and work harder to try to get quantitative estimates for the spontaneous segregation of these fission and fusion events. But it's an interesting phenomenon that comes up naturally in these when you look at the effect of non-equilibrium fission and fusion on the shapes of membranes. Okay, so I'll go on and describe how is it that that we analyze these complicated sets of equations. And one does that using perturbation theory. And the way to do it is to say that I expand. You first determine the steady states of these equations. You look for simple steady states which are homogeneous and spherical. But these are non-trivial steady states in the sense that these are spherical, homogeneous steady states in the presence of activity. Okay, so these are real active steady states. Then I ask whether I make perturbations on it, and I make small perturbations about the spherical shape, and ask whether these perturbations are stable or not. Okay, so the kind of perturbation that we'll do is we'll do a perturbation on the mass, okay, the mass influx, but will not perturb the shape, and we'll ask whether perturbations of the mass influx give rise to instabilities in the shape. Okay, so this is the program. Again, we look at the steady state shapes, which we consider to be homogeneous and spherical. We'll then make small perturbations about this and ask whether the resulting perturbations are stable or not. Okay, so this is what we do in pictures.
Can I ask a question?
Yeah.
So when you say mass influx, do you mean something like the mass being transferred per unit time?
That's right. I'll say exactly what I mean here in this picture. So we start with a homogeneous steady state with isotropic flux. Okay. And then we'll add little more material here. Okay. The rate at which you add material here is going to be slightly more than this isotropic flux here. And we are going to remove more material here. Okay. We'll do it in such a way that the net mass is conserved. Okay, so I'm just changing the, making the flux, the mass flux slightly anisotropic. Okay, and so this is my perturbation, and I'm going to ask whether this kind of perturbation leads to instabilities in the shape. And what we find from a perturbative analysis is that this kind of this very specific mass flux perturbation gives rise to a spontaneous drift of this Golgi membrane. Okay, it gives rise to a spontaneous drift. It also gives to a flattening of this membrane and gives rise to tubulation. Okay, so indeed, this is what we find. We find that that there is a phase diagram in the size of the Golgi, the size of the unperturbed Golgi, versus the imbalance between the fusion and the fission rate. And it says that if I make the fusion and fission anisotropy ever slightly anisotropic, that is, if I add a little bit of mass, increase mass here and remove a little bit of mass there, then if the size of the Golgi is large enough, then this Golgi will drift, will move in a particular direction. Okay. The way to think about it is what I've shown here. This is a kind of Marangoni effect. So drawn here is the unperturbed homogeneous spherical Golgi, onto which I'm going to put in this slightly anisotropic perturbation. So I'm going to add more material here, and I'm going to remove some material from there. Okay, and in such a way that the total amount of material is added and subtracted is 0. Okay, so I'm not changing the mass of the unperturbed, the total mass of the unperturbed sphere. So
Madan.
Yeah,
Madan. Is there a momentum transfer in this process?
That's right. There is. So because as I said in the one way to this thing is there is okay. There's a short answer. And that is the description I gave, that you need to remove in order to bring the vesicle onto the membrane, onto the Golgi membrane. I need to remove the water from the lubrication layer in between. Okay. And so you need to Okay. So there are shear stresses that develop in this momentum transfer.
Okay.
Yeah. So when I add a little material here, I'm going to reduce the tension, the membrane tension. And when I remove material from there, I'm going to increase the membrane tension. So there's a gradient of tension along the membrane, which drives the Marangoni flow. Okay. And these here, what I've drawn here in the arrows, are the flow lines of the fluid, which is in contact because the fluid is in contact with the membrane. These are the flow lines of the fluid, very similar to what Christina showed. And these flow lines that make this Golgi membrane drift in a direction as shown by this arrow. Okay. So it's kind of Marangoni flow. And what we can do is, by going to higher order in perturbation theory, actually get a formula for the net velocity of this moving Golgi. Okay. So this one, yeah.
So why this? I thought it's a pressure versus the flux across the membrane surface. Why should it be? Why the pressure should be asymmetric about 0?
Right. So this is a dynamic pressure. So this pressure it's not the same pressure that I talked about when I was describing the Helfrich energy. This pressure includes effects coming from fission and fusion. Okay. So let me not discuss this situation. This would happen when this should actually be thought of as being stresses. So this delta P here is the fact that you've got more fusion than fission. So the stress coming from fusion is more than the stress coming from fission. Okay.
That doesn't say anything about why the curves are asymmetric.
Which is asymmetric part?
Okay. I understood.
Okay, we can talk later. But I didn't understand what the flow lines here are. Okay, we'll discuss this later because I didn't understand the question.
Sure.
Yeah. Okay, so in addition to spontaneous drift that you also get a flattening of the membrane, and this is again because of the active forces. If you put in a perturbation which has a mass influx perturbation which has a quadruple symmetry here, that is, I add mass here. I add mass along these two regions, but remove mass from these two regions. You find again, because of the gradients of stresses, that a spherical Golgi will distort into this sort of flattened chapati shape. Okay? Similar considerations will show that non-equilibrium forces that you apply because of fission and fusion gives rise to spontaneous tubulation, and the number of tubules that you get is given set by a balance between bending rigidity and this active stress quadrupole moment. Okay, so the bottom line is that any kind of even the slightest asymmetry in the mass influx will give rise to shape instabilities. The shape instabilities correspond to spontaneous drift of the Golgi membrane, a flattening, and the tubulation.
Madan, there's a question from Shakuntala Chatterjee. Does the membrane shape change also in these different phases?
Yeah.
Does the membrane shape change also in these different phases?
Yes. So the membrane. So what we find, the membrane shape typically gets flattened and is tubulated like this. Okay. This is in this phase, in the phase where the fusion flux rate is slightly more than the friction flux rate. Is that okay?
Can you point to the phase diagram? Can you point to the phase diagram when you?
This is the phase diagram. Yeah.
Okay.
Yeah.
Yeah.
And so when the size of the membrane is large enough compared to the RC, which is set by the balance between surface diffusion and influx, then I can't see the pointer. Okay. Then in this regime, there is a spontaneous drift, there is a flattening, and there's a tubulation. Okay. Okay. So this is so this phase diagram tells you that as you move along the imbalance between the fusion and fission rate and the size of the membrane, you start getting different instabilities. Here you pick up a L equals 1, namely drift instability. As you go along this direction, you start picking up higher and higher instabilities. Okay, the larger the L is, the more tubulated the membrane becomes. Okay, is that fine? Okay, these kinds of shapes were also, we had done work long ago with Sunil Kumar from IIT Madras and his student Ramakrishnan, where we ignored hydrodynamics and did a numerical simulation using a dynamical triangulated Monte Carlo simulation to see whether the effects of adding and removing particles in a non-equilibrium manner drives shape changes. And typically we do see here, as you saw here in this particular case, that in the presence of fission and fusion, typically you get these flattened structures, okay, with tubulations as I'm showing here. And the moment you stop the agencies of non-equilibrium forces, you get a spherical shape. So in fact, indeed, non-equilibrium forces do give rise to such flattened architecture. I should remind you that this calculation, this numerical calculation, was done without including any hydrodynamics, and therefore cannot get the spontaneous drift instability. Okay. Maybe what I'll do now is to address the following question. So far, we've been talking about non-equilibrium assembly of a single Golgi cisternae. Okay, but remember, the Golgi cisternae has EM pictures of the Golgi look like this, which show a stack of Golgi membranes which are adjacent to each other. Okay? And the real goal of would be to try to understand how is such a stack of Golgi cisternae assembled. Not just a single Golgi cisterna, but multiple stacks such as these. Okay? So how does one assemble system of Golgi cisternae in the presence of a finite trafficking current? Okay? And indeed, what one wants to ask is what controls the size, shape, and relative positions of these different cisternae and the number of cisternae. Okay. Now, this has been, of course, dealt a lot with in standard biological textbooks. And what you read in biological text in textbooks on biology is two definite ways in which this entire system of Golgi is organized. These two models are called vesicle transport model and cisternal progression model, and they are schematized as shown here. So these Golgi cisternae, as you say, are stacks of Golgi cisternae situated between the source, namely endoplasmic reticulum, and the sink, namely plasma membrane. And in the vesicle transport model, they are thought of being stacks which are subject to incessant fission and fusion events as shown. However, in the cisternal progression model, they are thought as being dynamic objects. That is, tiny vesicles which emanate from the ER fuse together to form the first Golgi compartment, like so. You saw the birth of a Golgi compartment of a cisterna there, which then moves ahead, drifts towards the plasma membrane. Okay, and a new Golgi cisterna is created in this wake, and it's a moving cisternae, which is like a treadmilling of cisternae, and eventually these cisternae move towards the plasma membrane, disintegrate, and fuse with them. Okay. So these are two different architectures or models that biologists have come up with to describe the organization of the system of Golgi cisternae. And while looking at this remarkable model of cisternal progression, one should ask what is the driving force for the movement of these cisternae. And our contention is that the spontaneous drift instability that I talked about, which is a result of non-equilibrium fission fusion processes, is a way to understand the drift that is envisaged in these system models.
Madan, this question. So, what is the cell biological evidence based on which this biologists assemble these two views?
Right. So till some maybe 10 years ago, the evidence was simply that the size of these tiny vesicles, they are around 50 nanometer, 100 nanometers, but there are huge molecules like collagen which gets transported along these the Golgi, and these tiny vesicles can't encapsulate these huge molecules. So the idea was the first motivation for saying that maybe these huge molecules don't escape, don't get transferred from one Golgi cisterna to the other via these tiny vesicles, but they actually move in this cisternal progression manner. Subsequently, more recently, people have actually visualized this movement in a very clever manner in budding yeast, and this seems to be the only that has been subject to such kind of high resolution imaging. And in these in budding yeast, which is just one particular organism, there seems to be evidence that of movement of cisternae. Okay. Quantitation of the movement has not been done, and so these would be experiments that that one would like to see and compare our theory with. Is it okay? That's the only system. Okay. Okay. So now the question, the question before trying to address what is it, how do you arrive at a non-equilibrium self-assembly of the system of Golgi cisternae? Before we address this question, we should ask the following: what indeed sets the number of Golgi cisternae? Why is it that there are 3 or 4 in humans and something different in other organisms? Okay. Indeed, so I repeat the question here. What sets the number of cisternae? Indeed, the number of cisternae can vary from organism to organism. In mammalian cells, it's typically 4, but in many plant cells, there are a large number of cisternae, around 20. In green algae, it turns out, we are told that there are around 100 cisternae. Okay? So what indeed sets the number of Golgi cisternae in a cell? Okay, what is the driving force that determines cisternal number in the cell? Okay. And for a long while, at least the one theoretical model to address this question claimed that the number was decided by purely membrane mechanics, namely the interplay between curvature elasticity and membrane adhesion. I believe that is not correct, because the membranes in many of these cells are roughly the same. Okay, so the bending modulus and the adhesion energies are typically the same, and I don't see how that could give rise to the large variation in the number. For people, even I think this is supported by some biological evidence, is that the number is actually set by the function. And the function that I'd like to talk about is the chemical processing of proteins that are created in the endoplasmic reticulum and transferred from one Golgi cisterna to the other. Okay. This chemical process is called glycosylation, and what happens is that proteins that are created in the source, namely the endoplasmic reticulum, are transferred from there to the first Golgi cisternae, then to the next, and at each stage, the enzymatic processes go to modify this protein. Okay, when the cell keeps adding sugar groups onto this protein, making it a very elaborate structure, and this is then displayed on the cell surface, like I show here. Okay, what is the consequence of this? There are many consequences of this, but one of the interesting consequences of this is that this display of glycans is a marker of cell type identity. Okay, different cell types, even for instance, in humans, you have 200 different cell types. The different cell types have different glycan distributions. These are called glycans, and they have different glycan distributions on the cell surface. And this indeed is an external signal that the cell displays, which announces its identity. Okay, and what we believe is that is the fidelity of this information that is created by the cell for a specific purpose of announcing its identity that is responsible or is the driving force for the number of cisternae. Okay. And the way we analyze this is the following: that if you imagine you have a complex organism such as the human being, which has 200 different cell types. In order for me to to differentiate between the different cell types, the glycan distribution of these different cell types have to be significantly different for me to distinguish one from the other, for me to discriminate between the different cell types. Therefore, the glycan distribution should be fairly complex. It can't be a simple Gaussian. Okay, given this, we say let me try to write down a physical theory for how chemical processing happens in the Golgi. The theory would involve the production of the proteins from the source, ER, the transfer of the molecules onto the first cisternae, chemical reactions, namely enzymatic chemical reactions that happen in the first cisternae, the sequence of chemical reactions that happens in the first cisternae, transfer to the second cisternae with a given rate mu, chemical reactions that happen there, and so on and so forth. And finally, the display onto the cell surface. Okay? So one can write down a set of a chemical and a transport network which describes the transformation of proteins from the ER through the Golgi onto the plasma membrane. Okay? And if I know the parameters of this chemical and transport network, which will, of course, depend on the number of cisternae I have in the system, then I can tell you something of the complexity of the glycan distribution that I produce on the cell surface. Okay? So what we find is that having more cisternae, okay, more number of cisternae, and slower transport rates, intercisternal transport rates, okay, increases the complexity of the glycan distribution that you display on the cell surface. Okay, which means that if I want this is the driving force. The evolutionary need for you to create complex glycan distributions is the driving force for having high number of cisternae. Okay, and so the number of cisternae is tied to the complexity of the glycans that I want to create, which in turn is tied to the chemical processing dynamics that I have in the system. Okay, this kind of analysis has been articulated in great detail in this in the following preprint that we just put out some time back. Okay, so the bottom line of this is that the dynamics of non-equilibrium assembly of the system of Golgi cisternae should include not only the non-equilibrium membrane mechanics, okay, of how these cisternae are formed and the fission and fusion processes, but also the chemical enzymatic kinetics of molecules that are processed in. Okay, and is this combined non-equilibrium mechanics, namely membrane mechanics with chemical kinetics, that should give rise to the non-equilibrium self-assembly of these of the Golgi system. So that has been our take. Now, this, of course, is a complicated model to construct, and we have made very baby steps in this. And the first step that we did was in collaboration with Mustansir Burma and Bani Sachdeva in a series of papers that were written, which is a very sort of crude and simplistic model of the chemical reaction. The model is a set of transport equations, which with a source, namely the ER, okay, with a source which spews out little tiny vesicles at a given rate, K in, okay, and a sink which accepts, namely the plasma membrane, which accepts tiny vesicles. And on in between, the space between the source and the sink, these tiny vesicles, which have a certain chemical character, can fuse with a certain rate and fission out. Okay. Then we ask, what is the steady state configuration of such a dynamical system? The dynamical system being fission and fusion rates, which depend on the chemical on a variety of things, namely the mass of the cisternae and so on. Okay, so these are what we call chemical kernels, and they are given by the so-called Michaelis-Menten reactions that I talked about here. Okay, so by specifying the form of these fission and fusion rates, which are in principle mass dependent, mass of A mass of chemical species A, B, and C, and so on, one can derive a set of transport equations and ask what are the steady state configurations of this system. Okay, so this is the dynamics. As I said, it's a master equation for the rate in which chemical transformation happens and the rate at which mass changes. Masses of A, B, and C change. Okay, with the source and the sink. Okay, so what is the result of this non-equilibrium mechanics and enzymatic, this combined dynamics, which includes non-equilibrium mechanics and enzymatic kinetics in the simplest picture? Okay, we looked at two possible cases. One in which there is a spontaneous drift of these Golgi cisternae, as I described to you earlier. And the other cases where there is no spontaneous drift. Okay, that is some way in which I hold the cisterna to prevent it from moving to the right. Okay, so in the presence of a cisternal drift, what you find that at steady state, the spatial distribution of masses of A, B, and C are as shown here. Okay. What this says is that if I fix my spatial position, the spatial position being the distance between distance from the source. Okay? I'll call the distance between the source and the sink as L, and the relative distance between the source and the mass here as being x divided by L. Okay, so this is what I plot here: x divided by L. Okay. So what we find is that if I fix the relative distance from the source, then you find that at a fixed relative distance, you get a mixed cisternae. That is, the cisternae will have some mixture of A, some mixture of B, and a little bit of C. As you move closer to the source, you see there's predominantly A, a little bit of B, and hardly any C. But as you move away from the source, you find that you get more of B and then more of C. Okay, but the point is that in steady state, the cisternae here are not pure in the sense that they don't have pure A, pure B, pure C, but they have a mixed chemical composition. And indeed, that this is just one time snapshot. As a function of time, this keeps changing with time. Okay, the probability distribution of this is fixed, but if I look at microscopic realizations, they are constantly changing in time. Okay, so this, in fact, this would be the prediction of the assembly, of the nature of assembly of cisternae in the presence of a cisternal drift. When you don't have any cisternal drift, that is, you have some mechanism by which you prevent the movement of the cisternae, then you find that indeed that you generate large masses, and the masses are predominantly A, close to the source. The masses, and then you find a mass B, which is slightly away from the first mass there, and then C. You can see that the cisternae now are discrete, and they have pure masses A, B, and C. Okay? So this is an interesting prediction. It predicts that if you include cisternal drift, then you necessarily have mixed cisternae. If you prevent cisternal drift, then you have pure cisternae. Okay, and what is interesting is that the distance between cisternae here is not set by membrane mechanics, but is actually set by non-equilibrium processes of chemical reaction rates and fission fusion rates. Okay, so it's the non-equilibrium timescales, namely the chemical reaction dynamics and the fission fusion dynamics, that sets the relative position between cisternae. Okay. So these are features that indeed could be tested experimentally. Some of these are no, for instance, in response to Shriram's question, I said that in fission, in budding yeast, which is the sole example of cisternal drift mechanism, you do find that vesicles have mixed cisternae. That cisternae are mixed in their composition. But as I said earlier, much more work needs to be done. Much more higher resolution experiments need to be done to be able to test these predictions. Again, the predictions are being that for when you allow for cisternal drift, which is generated by having these non-equilibrium fluxes. If you allow for cisternal drift, then you find that cisternae have mixed chemical composition. If you prevent cisternal drift, then you find that cisternae are discrete, like so. They are well defined in terms of their chemical composition.
Madan, there is a question from Maitreyi.
Yeah.
Does experimentally modulating glycan complexity influence the assembly or number of cisternae?
Right. That's an excellent question, and this is something that I've been talking to Ajit Warki about. Apparently, no one has done this experiment, and this is a very interesting experiment to do. So at the moment, I don't know the answer to this. However, let me just say the following: that it is a difficult experiment because the number of Golgi cisternae is set by some evolutionary requirement. Okay, so it's not clear what is it in the chemistry that we need to remove in order to see this reduced number of cisternae. But it is an interesting question, and it would be interesting to try to understand this in a proper way. Yeah. Okay. So as I said, this was a very crude model of chemical dynamics and transport. At the moment, we're trying to add in slightly more sophistication to this model, so that we will be able to talk to our experimental colleagues in terms of what kind of perturbation that you would like to do in the chemistry in order to see a change in the number of cisternae or in changes in the dynamics of changes in the non-equilibrium dynamics of these membranes. Okay, and one of the questions that we are that this is given right through is the following. This in fact is very closely, this non-equilibrium assembly of the system of Golgi is very closely tied to the following question of how does the cisternal size and the number scale with cell size. If I increase the cell size, let's say 2 times, does the number of cisternae change? Does the number of cisternae double, or does the cisternae increase? This is a question which is, I think, very fascinating, and we are currently working with Vaishnavi Narayan from IISc to try to investigate this in the context of chemistry. I think I'll sort of end my talk here and summarize it. But I've tried to discuss the non-equilibrium assembly of a system of organelles, in this particular case of cisternae, which are subject to non-equilibrium flux of fission and fusion. And it's not only the non-equilibrium assembly of a single membrane bond, but system of organelles that we've been interested in. And this, as we said, involves the interplay of the dynamics of fission and fusion, dramatic dynamics of the chemistry, and I believe that this is a very and they're very, very open challenges and questions, both in terms of experiments and theory. And one of the things, one of my pet dreams is to see if one can synthetic realizations of non-equilibrium assembly of structures. It may not be membrane-bound structures. It could be large droplets. But the idea would be that you want to look for an assembly of a system of large droplets which are subject to fluxes of material. On this, I've been working a lot with Shakti Tutupalli, my colleague at HCBS, and Patricia Bassaro at Curie, and Pearson at the Curie Institute.
Madan, there's a question from Neelima. Is detailed balance violated for all the cases here?
Yes, absolutely. So these are strongly violating detailed balance, both in the chemistry and in the transport mechanisms. Yeah, I mean, for instance, the fact, just in this cartoon, the fact that I'm predominantly transferring materials towards the right, okay, implies a violation of the detailed balance. So at every step, I'm violating detailed balance both in the chemistry, as I show here, A going to B going to C. There are no backward arrows, and in the transport. Okay. And similarly, that was true for the non-equilibrium membrane mechanics that I talked about at the earlier part of the talk. Yeah. So with that, I'll conclude and acknowledge the many collaborators in this sort of project, and this ideas were thought of long ago, 2000, when Shriram and I were working on active membranes. The earlier avatar of this was with my student Shoroshich, and then Kripa Gauri Shankar. The more recent version of this was done here by Alex Rautu and Richard Morris. They were postdocs with me at the Simon Center. And now Alex Rautu is in the Simons Foundation in New York, and Richard Morris as a faculty position in Australia, in EMBL in Australia. Okay, the active fission and fusion numerical studies that I talked about was done in collaboration with Sunil Kumar when he was at IIT Madras, and his student N. Ramakrishnan. The organelle biogenesis, the transport equations that I talked about, which describe the non-equilibrium assembly of the system of organelles, was done in collaboration with Stansel Verma and Himani. Finally, the sort of glycosylation, the chemical processing of glycosylation and its relationship to information theory was primarily the work of Alkesh Yadav, my student from RRI, and in collaboration with Garuda Iyengar. And I'd like to thank funding from the Simons Foundation of the US and the JC Book Fellowship from DST. Thank you, and once again, it was a real honor to give this talk here, and I welcome any questions that you might have. Thank you.
Thanks, Madan, for a wonderful presentation of a large body of work. You tried to compress it in a short time span. Questions from the audience?
Can I ask one question?
Yes.
Please.
Hi, Madan, Vivu here.
Hi.
Just some curious question. The kind of force you told about 10 piconewton, I mean, so what kind of things are responsible for drifting this vesicle fusion? For example, polymerization force are typically of the order of few piconewtons. So you may need few filaments to make this vesicle propagate toward this for fusion. So that is first kind of question. And second question is, this kind of the cytoskeletal interaction, I would imagine they will be pretty anisotropic. So will there those kind of interaction will also have a say in this drifting of this drifting mechanism? So would you like to comment on that?
Right. Okay. So thanks, because some of that part. So let me just go back. Right. So let's go to the cytoskeleton. Right. Yeah. Okay. So the way the vesicles come close to the membrane, adhere, and eventually fuse is facilitated by motors which drive on microtubules predominantly. Okay. And so that's the first step, that vesicles are brought to the vicinity of the Golgi using active motors. Okay. So it doesn't happen by polymerization kinetics, but it happens by motor forces. Okay. Once it is close to the once it is close to the membrane, then these molecules here, which are called snare proteins, in conjunction with something called RABs, which are GTPases that I talked about, will go to dock this. Okay, and this again requires energy. Okay? So it not only has to, the motor proteins just bring it close, but doesn't make it touch the membrane. You require other molecular processes which will go to pull it onto the membrane and make it fuse. Okay? So these are so it's mainly from motor-driven forces and these GTPase-driven proteins which assist in addition. Okay, that is the first. And what is the next one?
Yeah, the next part I was talking about the cytoskeleton interaction will be a bit anisotropic. So will that also have to say with the drifting mechanism?
Absolutely, yeah. So okay, so so let me just say. So according to the calculation that I talked about, I was arguing that as long as the size of the Golgi was large enough, then any kind of anisotropy in the fission and fusion will drive the drifting motion of the Golgi. Okay, and as I said, an explanation of that is this kind of Marangoni phenomena. The physical insight of that is this Marangoni phenomena that I talked about. Now the question is, do you see that in experiments? Okay, as I was telling Sriram, that this has only been seen in budding yeast so far, but in a lot of human cells, they don't find the movement of cisternae. So in fact, the question is, does the cell have mechanisms in which to suppress this drift? And I believe that this is where the cytoskeletal interactions play a role. So the cytoskeleton, which forms a scaffold around this, around the Golgi, and prevents by sort of confining it, prevents any tendency for the spontaneous drift to occur. Okay? So this, of course, the binding of the Golgi membrane to this cytoskeletal scaffold is also mediated via these proteins, okay, they're called matrix proteins. And so now you could ask, what happens if I disrupt these matrix proteins and therefore locally get rid of the cytoskeleton? Do you see a spontaneous drift of this membrane? It turns out that when people did that, that's a difficult experiment again, because all kinds of things happen. The moment they get rid of the matrix proteins and the local cytoskeleton, they find that the membrane just spontaneously disrupts. It just breaks up into little fragments. And that's because I think you're also affecting the fission and fusion process. Okay, so in the absence of fission and fusion, this whole thing, or in the absence of fusion, the whole thing just comes out and breaks up. Okay, so
yeah. So thank you so much.
There is a question from Shakuntala Chatterjee.
Yeah.
Is anything known about the dynamics of tubulation? For example, can you calculate some dynamical exponent by monitoring the structure formation?
So, okay, you certainly can't do this in vivo, but let's say in vitro, there are many mechanisms by which tubule formation occurs. In the calculation that we have done, the rate at which tubulation happens is exponentially fast because it's a linear instability. So all you get is an exponentially growing mode. Okay, but experimentally, so people have looked at tubulation in membrane systems where you add polymers. Maybe Guru might actually know more of this than I do. And there again, you see the growth of tubules. And in fact, you see all kinds of tubules. For instance, you see twisty tubules and so on. As far as I know, people have not looked at the dynamics of tubulation. What people can do is look at the tubule sizes, and that there is a fair amount of understanding. And the size of the tubule is set by the bending modulus and the membrane tension. But I don't know of any work where they look at the dynamics of tubulation. Guru, do you know of any?
Not off the top of my head. I'll have to look at. So this is really looking at that as a polymerization process then?
Yeah. So usually it's pretty fast. So I don't think it's a slow growth of tubulation, from which you can extract dynamic exponents.
No, I'm sorry. I don't know of it. I mean, I'll have to look it up. Just some speculation, but yeah.
There is another question from Professor Bhaskaran. Is there any connection at level of mechanism between vesicle attachment and virus attachment?
Yes, absolutely. Yeah, absolutely correct. So, okay, so the way viruses, of course, and there's been fair amount of work, huge amount of work on this. But the way, so viruses generally come from the outside and they bind to some receptor on the cell surface, and then they typically enter the cell via a process called phagocytosis. That is, there's a membrane deformation, which then brings in the virus and the receptor on which it binds, and that phagocytosed vesicle gets then incorporated within the cell. The mechanism by which the details of the mechanism by which that happens is very different from the fission and fusion process that I was talking about in this lecture.
Thank you, Madan. It was very nice.
Yeah, thank you. A lot of that can be understood by equilibrium physics.
Madan, I have a question. How does the unhealthy cell compare with a healthy cell in this?
Right. So you can ask, for instance, in a diseased condition or something.
Yes. Yes.
Yeah. There are many ways in which you can make a cell unhealthy. But for instance, if you and this is a very good question, because this is in fact something that we will be studying with Ram Ray, who's a collaborator at ISC. It turns out that that I'd like to point to this picture here. What I wanted to state here is that the distribution of glycans, or these sugar-coated proteins on the cell surface, is a marker of cell type identity. Okay, that is, different cell types have different displays of glycans, different distribution. But it also depends on the niche. Okay, that is where the cell type is formed. Is it formed in its host environment, or is it in some other environment? And in many disease conditions, especially in cancer, metastasis drives a cell to some other niche, okay, to some other environment. And in the process, it changes the glycan code. So the dynamics of change of the glycan code is something that is very interesting. It involves, again, the dynamics of transport and chemical processes we talked about. And this is something that we are going to be working with Ram.
Okay.
Yeah, but the change in the glycan distribution in disease condition is a very, very big and important field of study in that.
Oh, okay. Thank you.
Madan,
yeah.
I'm not understanding something fairly elementary.
Yeah.
You have, you say humans have like 4 cisternae, plants have 20, green algae have 100 or something.
Yeah.
So, I mean, I thought you would need more cisternae to do more of a comparison and discrimination among cell types. So it's not like that, is it? I would have thought that the processing of information might require more stops along the way.
Correct. That's exactly right.
So I must not have understood mechanism.
Yeah, absolutely right. So in the story I was trying to give you, the only function of glycans that I talked about is glycans as a marker of cell type identity. Okay, and so given that as a sole function, then clearly, then what you need is that the more cisternae I have, the more complex a distribution I can make. Yeah. However, biology being biology, the functions of there are many functions of glycans. For instance, cell adhesion has to do with these glycan proteins. Okay? Because plants, so plants have an enormous diversity of proteins that sit on the surface, cell surface, because they are used in cell adhesion, in providing plant rigidity, in the immune system of plants can't run away when there is some pathogen close to them. They have to deal with it. So the immune system and all that is very complex and different from ours. So, a lot of these molecules are these host of molecules that are needed is so there's a huge amount of glycan diversity which goes to do these other functions. Okay, so I'm just giving a very simplified story here. It's not. It's one of the main functions of glycan.
But then why so many more for green algae?
I have no idea.
Green algae are more evolved than us.
That's right. Okay. I have no idea, but this is really crazy. The green algae have 100. I don't know. Yeah.
Sorry, I had another dumb question. Coming back to the structure of the goal, this whole layered, the structure of the
system
of the
system.
Yeah, right. Yeah. So you said it's not set by membrane physics at all, but even the communication between these different, if you think of these as roughly sheets connected by necks or something. One way would be to think that you have a lamellar phase and you have a few neck defects connecting them. And you have some mechanism by which these lamellae talk to each other. Is it nothing like that, or is it a little bit like that?
So indeed, that's really correct, Sriram. The paper that I referred to, which deals with the membrane mechanics of this, is by Svetlana, and he indeed looks at. Imagine that you have stacks next to each other. You just write the total energy as being the curvature energy for each, plus an addition energy between these. Okay, and so then the parameters that you have are the bending modulus and the addition strength, and depending on whether bending modulus is very large, it costs a lot of energy to have multiple stacks, and so the number of cisternae will be small. If the addition energy is larger, then you have many stacks. But the only trouble that I have with this is that that is too generic. It is a model which will give you a number, but the bending modulus of membranes is not very different. It's around 20 kT, in plant cells. Yeah. So I just feel that while it's a plausible physics model, I think it has nothing to do with the with what is happening in the world. Moreover,
there are models of interacting surfaces where the contact between them is set not by, I mean, where the spacing between them can be set by something that evaporates from one and goes to the other, that kind of thing, which can be, you can get. Just a second.
Yeah.
Sorry, there was background noise. I'm just wondering, are there other mechanisms for setting the spacing between these layers?
Yeah. So, right. So I guess you're thinking of sort of the active version of Helfrich kind of model, right? That is, you have stacks.
There are ones where it's not even membrane fluctuations, but something much more remote. Like when you have these bright phases in flocking models.
Yeah.
You get a period, and the period seems to be set by God knows what. And since it might be set by some exponentially decaying interaction of stuff evaporating from one and adhering to the other. So not by bending fluctuations, but by actually much more tenuous kinds of interactions, which could include stuff being transported. At least the stripe phases in flocks have that.
Yeah. Maybe it's worth thinking. I suspect my sort of gut feeling is that that understanding the number really requires this coupling between the chemistry. But I guess in the model for this thing, you would also include the chemistry, chemical processing, right? Yeah. So from what we from one of the predictions that we make is that spacing between the cisternae is set by kinetic parameters alone, and that's an intriguing prediction, which I feel has scope of being testable, right? And so I think what I would really love to see is these synthetic, assemblies of these membrane organelles using charged lipids, kind of self-assemblies that had looked at some time back. What she managed to look at synthetic ways in which to create stable, a single stable membrane organelle in the presence of fluxes of charged lipids. But now to extend that to a stack of membranes would be an interesting thing to do. And there I think one could address questions that you have asked.
Cool, thanks.
Are there any more questions?
I don't see any further questions on the YouTube stream as well.
Okay, so we'll. I would like to thank Madan for a wonderful talk once more, and we would now be concluding this symposium. Let me. Before we conclude, I, on behalf of the organizing committee and the Department of Physics, IIT Madras, wish to thank Professor Rodam Narasimha and Dr. Nilima Narasimha for creating this endowment fund in memory of Aditi Simha. On behalf of the organizing committee, I thank Professor Setupati, the head Department of Physics, IIT Madras, for extending full support at every stage since the inception of this event. I thank Varun for help with the website and the department staff for ensuring that things were running smoothly in the background despite the hardships imposed by the current situation. The organizing committee also wishes to thank the speakers once again, all of them, for readily accepting our request to participate. The organizing committee also thanks colleagues of the Department of Physics for their inputs at various stages. We as a whole of the Department of Physics would like to thank the audience for joining us on the Saturday morning. Now it's an afternoon, and also for the active participation throughout. We really hope that the next year's event would be a regular symposium. We'll be looking forward to meeting you all in person. Stay safe.
Thank you.
Thank you. Thank you once again to everybody.
Thanks, Madan. Thanks, everyone, for being here.
Yeah, thanks, sir.
Yeah, have a good weekend.
Thanks, everyone. Thank you. Thanks, Guru. Thank you. Thanks to everybody.